Okay, I hope I'm live. Hi all, am I live? Am I live? Let me, whoops, I gotta get this. Why did YouTube put that on top? I don't want that on top, I want this on top. Thank you. That's crazy. Ever since I had to start streaming this way, it makes my life a little bit tougher. All right, I needed to get my display so I could see what I was doing. Hi all, can you see me? Hear and see. That's the number one thing. Yes, yes, hear you and see you. How's my volume? Is my volume good or do I need to crank it? Because I can. As a matter of fact, I'll boost it just a little bit because everybody always complains that my volume is too low. So I'm going to crank it up just a smidge because I do not have anyone monitoring my audio right now. And I hope that this isn't too, hopefully that's a little bit louder. Okay, good, excellent. Volume is okay, awesome, all right. Yes, everybody who doesn't already know, I am a one-woman show, so anything that goes wrong is my fault, and anything that goes right is also my fault. So I guess there's good and bad, right? So we are starting, for those of you who have never seen a mini course before, we are actually starting a really neat phase of all the mini courses that I've been doing. And I've been doing them for, my goodness, over, 2-3 years now. And there's actually quite a few of them. We've actually gone through 2 different sets. We've gone through the space weather basics, which basically talks about the sun and all of the phenomena that come out from the sun. And we've now also discussed the near-Earth system all the way down to the ground. And these 2 systems act very differently. So if you know one but not the other, you really kind of are hurting when it comes to understanding how space weather actually impacts Earth. So it's taken us a very long time to finally get here. But now, if you have managed to stay up with all of the courses over the course of these several years, you have a very detailed understanding, at least conceptually, of how space weather impacts Earth. And what's cool about that is that it will give you a unique understanding of some of the stuff we're going to talk about today. And I will do my best to make sure that all of this stuff is, reasonably accessible to even people who've never done a mini course before. But there will be things that you might get lost in, especially when I start talking about different types of phenomena, like difference between a radiation storm and a coronal mass ejection, because we will see those types of effects. But you really need to understand a little bit about that kind of thing to be able to understand how we deal with things like big events, like superstorms and Carrington-class events, which we're going to go into detail today. And then you get to a better understanding of, well, really the implications of what that means for us going into the future, okay? So, hello everyone. Nice to see Michael Richardson. Thank you, Mike, for being here. He is a moderator. He's probably going to do some very heavy lifting today. Be very nice to him. I don't have to tell this to anyone in the Patreon community. You guys are wonderful. But any of you others who decide that you want to troll or be mean to people in our family, please do not restrain yourself because Mike will kick you out. He is just the guy to do it. And so be nice to each other, right? This is a learning environment. People get things wrong, including me. So be nice to each other, please. That's why we're all here, okay? YouTube is a nasty enough place elsewhere. Let's keep this place friendly. Okay, and thank you, speaking of my family. They're all behind me. And if your name is not up here yet, that's just simply because I haven't been able to update this opening slide here over this last month. So don't worry, your name will be up here, I promise you. Yeah, let me do this. This is my VIP steering committee. As you can see, we've gotten quite large. All of these people, including the top tier, all of these people they help steer the ship. They help decide which way our community is going to grow. And I'm so grateful for them. They've become literally a second family of mine. And thank you so much, you guys, for being here. You definitely have made a huge difference in terms of what I do and what I prioritize. And I'm looking forward to more years to come. And thanks to all the mini course patrons. Like I said, if your name's not up here yet, it soon will be. These are all the people that help decide what course we're going to have, when we're going to have it, if they like it or not. They can veto. And then they also get all the abilities to ask questions both online while we're here, but also offline, and I answer their questions in our Patreon community. Yes, I will. For those of you who have asked me, I will start doing the subscription stuff on YouTube. I haven't. I apologize. It's just, I'm just so, I need to do a lot of stuff behind the scenes with YouTube in order to make that work. So that is coming, I promise. So you will be able to engage me there as well, because there's a lot more that goes on behind the scenes and a lot more in-depth analyses and discussions go on. So thank you to my Patreon family. I appreciate you all so very much. And I'm sorry, I'm going to just jump in. I want to say hi to everybody in person, but because I see all the chats going by. But whoops, this was supposed to come off. Hold on. I put these charts together last night, so obviously an animation didn't take. You're going to see some fun stuff, because this is stuff I don't even teach in my Millersville courses, but you have to bear with me if there are some late night mistakes here. There we go. Okay, so let me shut this door and we'll get going, because that's kind of distracting. So as you can see, we've loaded up the deck. We've stacked the deck, haven't we? This is one heck of a thing to talk about, to open up a course with, but that's how fun this course is going to be. We are going to begin with Carrington class events, and the reason for that is because what we're about to dive into, right, are some of the biggest storms in history. Now, the thing is that everybody automatically assumes, okay, the biggest storms in history, we know what they are. We've heard about them on YouTube and everywhere else. We're experts at it. They're mega flares, and they're kill shots, and they're micronovas, and they're power grid killers, and they're Armageddon from the sun, and they're God's wrath, and basically they're any space weather event that spells doomsday for Earth's weakening magnetic field. Oh Lord, we're going to go to, hell in a handbasket, and all the electronics on the Earth, your batteries in your car are going to explode, your computers are going to zap, right? Anything that's plugged into a wall outlet is going to fry. If you have a pacemaker or a diabetic, insulin machine on you, good luck, because they're just going to explode spontaneously. It's going to make you spontaneously combust. And really, raining cats and dogs, buildings are going to catch on fire, and everything else. That's a Carrington class event, right? I mean, look, even the Weather Channel, look at it. Fire and brimstone, right? This is what we look at and what we think of when we think of a Carrington class event. Pictures like this, right? I mean, this is supposed to be aurora all over, but my goodness, it looks actually like smoke. I don't know about you guys, but to me, this looks like smoke billowing out. Everything is just burning, right? This is a classic Carrington class event picture of our grids. Of course, the wires are going to light up blue with corona because they're arcing and sparking so much. Aurora is going to be everywhere, right? I'm not even sure what kind of aurora this is. It looks more like some alien energy, right? And not just that, but power grids are going to, the wires themselves are going to have massive explosions right at the towers. So God forbid you're some guy down here watching this, right? This is kind of silly. Don't you think they'd be fried? I mean, this is where their, pacemakers explode and their insulin meters pop, and, they just basically burn instantaneously. Or look at this one. Here's one where the sun is just, literally cooking with beams of energy, frying Earth with its, I don't know if that's particulate radiation or solar, massless photon radiation or what that is, but it's searing like an ant under a under a magnifying glass, right? That's Earth. And is that a definition? I mean, and all of this is associated with the Carrington class event, right? So you say Carrington event, and it is absolute mass panic, right? But is any of this a definition? Or, for matter of this, is that a definition of a Carrington class event? No, right? It's pop culture's definition. Yeah. So we're going to carefully look at how a scientist goes about, or many scientists go about, analyzing Carrington class events, and really what kind of definition do you come up with? Right? And it might be surprising. Okay, so we know that's not right. I'll keep these pictures up for fun though. Okay. So how would a scientist go about defining a Carrington class event? Well, from the classes that you've already taken, right? Do you do it by eruptive signatures on the solar disk? Or how these eruptive signatures, which are CMEs, right, coronal mass ejections? Or do you do it by how those eruptive signatures then propagate out into the interplanetary medium, right? Interplanetary CMEs, right? Those of you who have taken the courses know that these are not the same. They represent a similar phenomena, the same phenomena, but one is at the sun and one is as it moves out into interplanetary space, how it's measured, what happens to it, right? This includes all of the traffic that it reaches on the way to Earth. So those are already two different ways that you might be able to identify or characterize a Carrington class event from a space science perspective, right? From a physicist's perspective. Well, what about solar flare signatures, right? Those of you, again, who've taken the courses know solar flares are like MX, right? X23, X10, X82, right? Anybody who tells me, oh, that's a Carrington class event, it's an X25 solar flare that's reaching Earth that's going to cause major aurora. I'm like, oh, this person automatically doesn't know what the heck they're talking about. You don't have an X-class CME. You don't. You have an X-class solar flare, sure, but that's not the same as this. And it doesn't do the same things. Right? So solar flares. So now we have 3 designated potentials for a Carrington class event. Well, what about solar radiation storms, right? The particulate radiation signatures, also known as solar energetic particles. Again, those of you who have taken classes on this know that that's a totally different signature and it affects totally different things, right? But you can have really, really big ones where the astronauts duck for cover, right? And soon, aurora, space tourism and Mars colonists and all the others, they're going to be ducking for cover during storms like this. But does that necessarily mean you're going to get massive aurora? No. Does it mean power grids are going to die? No, not even close, right? Because all these 3 things here are radically different phenomena. They affect Earth radically differently. So, okay, well then do you define it based on the effects at Earth? Well, maybe. It certainly has been done many times, and we'll talk about the positives and the negatives of that. But see, automatically, if I flip back to this, look how qualitative and emotionally based this is, right? And every single person here, I guarantee, has heard these terms. If you are on YouTube, you have heard all of this, maybe ad nauseum, right? I sure have. But is that really a good definition, a quantitative definition? No. You have to investigate it in a slightly different way. Slightly? Well, I'm being nice. But it turns out, in fact, that Carrington class events and defining them might be a bit trickier than one would think, because it's not an all-encompassing thing. And so some of you who are very savvy might recognize already, as I walk out of the frame, I apologize to shut the door completely. Some of you might already recognize that, maybe, just maybe, one event may not fit the entire bill. Well, you'd be on the right path. So, scientists are quite savvy, and I have a couple of favorites of mine. If you recognize that I lean quite heavily towards some people and as opposed to others, that's just because I know them better. This was my advisor, Chris Russell. Janet Lumen is a good friend and colleague. Pete Riley is very respected, and I know him as well. He's the infamous, well, he'd probably say famous, but I say infamous because he's the one who said, we have 12% chance of getting a Carrington class event in the next 10 years. That was what published, I forget if it was published in Space Weather, I think it might have been Space Weather Journal, but wow, did that blow up. And I'm not even sure Pete expected that, but that became like the thing that everybody talked about for the entire decade last cycle. So if you don't know Pete, you probably know that particular statistic. And it was a very rigorous study. I mean, I'm not saying he's wrong, but what I bet he didn't necessarily recognize that the media was going to gobble that up like it did. So yeah, so that's Pete. And this is one of the anytime you deal with a Carrington class event, this is what you deal with. You deal with mass hysteria, right? Because everybody thinks micronova. Oh my goodness. So thanks to Pete, right? He had no clue, but he basically said, we have a 12% chance of getting this to the public. Which, you know, in retrospect, maybe not so fun, right? It's a bit scary. No wonder the media picked it up, right? But in actuality, it's more, which part of this are we talking about? Okay. So when you think about 12% chance of getting a Carrington class event, well, is it going to be the whole kit and caboodle, or is it just going to be a Carrington class in one of these areas? Okay. So already, hopefully, I'm kind of recalibrating how you look at what a Carrington class event is, right? And how we define them. And because I've never taught this before, if you see me pause, it is not because I'm scared. I did a live thing, I don't know, about I think the very last briefing I did, and we had, excuse me, we had a second radiation storm. We had a radiation storm that was ongoing, and then we got this blip where we started getting more energetic particles. And I paused and I was looking at that because I was saying, well, I had originally thought that was the energetic storm particle, you know, basically when the shock crosses Earth, okay, or the spacecraft at L1. And I paused because it stopped me because, you know, I'm used to seeing that peak. Well, we had that peak, but then we also had energetic particles at a higher energy. And I paused and I went, I'm not sure ESPs energize that much. They energize the fluxes, but that would only be in the low energy side. They wouldn't give us 50 to 100 MeV particles. He's really, really energetic. I'm like, I'm thinking inside my head, wait a minute, Tam, you may be wrong. That may actually be a second energetic particle, you know. So we have now 2 radiation storms, not just one. And it just happened to be timed just right so that it looked like it was this increase in particles that we get during the shock passage at Earth. And so I paused and I went, And I went back and I looked at the comments. And I don't remember who it was, but someone was in there going, oh, she's scared. Look how scared she is. She's scared. Because it's one of these micronova people, right? And I was just like, oh, just roll my eyes. Like, if I pause, it's because I'm trying to be thoughtful about what I say and how I say it so I don't mislead you, okay? And so that I don't get pelted with olives by the scientific community. Because remember, I'm not a YouTuber per se, right? I'm a scientist. I go to scientific conventions. There are scientists who actually watch these shows from time to time, if for no other reason than to laugh and giggle and eat popcorn. But they then will come back to me and tell me when they see me at these scientific conferences, you did this wrong, you did that wrong, you should have said it like this. And I'm like, oh yeah, you're right, shoot, right? So that's what's running through my mind. And I think it's apropos, I think it's important that I state this now and take a moment to state this, because what I don't want is, especially when we're talking about Carrington class events, I don't want anybody to sit here when I pause and think thoughtfully, because this is the first time I've taught this material. I don't want anyone to stop and think, oh crap, she's scared. She doesn't know how to tell us the truth. Oh, come on, give me a break. I'm being thoughtful because I want to give you the right food to eat, right? I want to give you healthy food, not junk food. Junk food is micronova and mega flare and all of this crazy astronomical stuff that happens at very young, very, hormonal stars, for lack of a better phrase, right? We can always humanize them and make ourselves understand that they're like angry teenagers who are going through puberty. And they'll shoot off these things. You can use those terms with those other stars. Our star is not that star. Our star is tired, as I've said 1,000 times before. Our star is a middle-aged star, right? It's just wants to go to work, get on the road. It wants to drink its coffee in the morning, read the newspaper, send the kids off to school, go to work, do its job, come home and watch a sitcom on the couch. That's what it wants to do. And so it's a very well-behaved star. So all of these crazy things are really, they're untruthful and they're junk food. And yeah, of course they're surprising and exciting and, oh my gosh, we have to live every day and seize the moment because we're all going to die tomorrow. Well, no, we're not. And hopefully this is going to get you to understand why. So when I'm thoughtful in my speech and I stop and I pause, it's because I want to give you the healthy food that you crave, okay? And so give me that moment to rephrase or pause and think without assuming that I'm going off the rails and scared to death. It's just not true. All right, enough of that. I get off my soapbox now. But I think it was important because, you know, anytime you have this on the screen, it's like a trigger for people and they begin to just freak out for no reason. Okay. So back to this. So Carrington class events are a very, I don't want to say, no, they're not protected. They're just a very well-studied, let's say well-studied class. A lot of people really enjoy them because they, especially scientists, because they oftentimes have very clear signatures and unambiguous consequences, as well as unambiguous signatures in all sorts of data, right? And so, and because they're the most impactful, and because there's a lot of money to study these level events, because they're the ones that have they're what we call the low frequency or low probability, high impact type of event. There's a lot of money to study them. And so they've been studied ad infinitum. You don't have to work very hard to find a ton of work on them. What you do have to deal with is a lot of them are historical. So a lot of them happened when we don't have a lot of data. So a lot of it is forensics analysis, right? So we go back and you'll see some of that when we start digging into this particular event. What we call the benchmark, the reason why we have them called Carrington class. But you'll also find that there's a lot of them out there, a lot more than you might think. It's not just the classic 1989 or 1859 event. There's a ton of them out there, and we're going to go through some of them. But what was neat about this particular paper was that this was a time of actually taking the class and actually trying to look at a particular type of predictor, okay? We go up to here. We're talking about now not impacts at Earth, but the thing that can cause the biggest impact, right? Because we're talking about power grids. If you recall from our classes, ICMEs and the ensuing geomagnetic storm that ICMEs cause. So I call these solar storms, right? When they hit Earth, they cause a geomagnetic storm, right? They make the Earth's magnetic field wiggle. There's all sorts of implications that happen with that wiggling coming down, propagating all the way down to the surface of the planet when it comes to power grids. Okay, there's lots of other stuff that happens during a geomagnetic storm too, but I'm just talking about how geomagnetically induced currents are caused. And so when you induce those currents in the ground and then they couple up into the power lines, there's lots of havoc and chaos and big destruction, right? Because it's our power grids. We don't want that. So that was pretty low-hanging fruit. Let's take a look at how do we define a Carrington class event using the storms, the ICMEs, which are the things that cause the storms, that cause, well, not this, but yeah, okay. So what they decided to do is they decided to, and I'm not going to go through the whole paper, but it is open source, so you can actually get it. What they decided to do was look at, and sadly, there's going to be a lot of like just graphs and things. So, this isn't the most eye candy of all courses that you're taking, but I'll try to make it more creative as we go. So what you're looking at is a very strange graph, and this is what on this axis we're calling it the observer flare angle. So basically, if you're looking at the sun and you have a solar flare, and depending upon where that source region is relative to Earth, right? So if I'm the sun, and this is the central meridian, right, along my nose, right? If I'm over here, I might be, this is 0 degrees pointing straight at you. If I have a pimple on my face, and that's where the solar flare is going to happen, okay? It's shooting at you, but it's not shooting at you from 0 degrees, which is right at my face here. It's shooting by some distance off, 10, 20 degrees over here, or 10, 20 degrees over here. We don't care which side. But if a solar flare is shooting straight at you from my nose, right? You draw a line from my nose to you if you're Earth, and that's the shortest distance, right? But if I'm over here, if the pimple is firing over here, not on the tip of my nose, but over here, this is really disgusting. That line that I draw from this cute little pimple, hello, to you is going to be a little bit longer, right? So their idea was, and I'll go into this a little bit more deeply when we look at how a coronal mass ejection kind of, moves outward. The idea is that if you are at the shortest distance between that solar flare, so basically central meridian, that solar flare is going to launch, I'd be careful. During the solar flare, a coronal mass ejection is launched. We don't need a solar flare to get a coronal mass ejection. But for Carrington class events, the CME needs to be extremely explosive, extremely like kicked out of the sun, right? How does that happen? How do you kick a CME out of the sun? Make sure you have a flare with it, because it gives it that extra, right? It's the propeller, the high-speed propeller on the back. It's a jet engine on the back of that thing to really goose it and make it extremely fast. Okay, so with Carrington class events, you're always going to have that because they're extreme. So if that solar flare, which is the propellant, boosting that CME that launches, the closest, if it's on the tip of my nose at 0 degrees, then it's going to have the fastest travel time, or not the fastest travel time, the fastest travel time, even if it's going the same speed, because it's got the shortest distance. If it's somewhere off of my nose, off of central meridian, then it's going to take longer to get to you. Because really that CME isn't blowing straight towards you. That CME is always blowing straight outward. Okay, got it? So as the sun rotates, right, so now if we just pretend the pimple's on my nose, as that sun rotates, I'm shooting off coronal mass ejections this way. Well, will some of it get to you? Yeah, it will. But it'll take longer because it's the edge of this thing, because its main thing is going out this way. So it will get to you, and we'll talk a little bit more about how that happens. But as that CME, as I continue to rotate as the sun and I'm blowing out CMEs, see, when I'm blowing it straight out at you, it's going to hit you soon. Much, much sooner than if I'm blowing it out here and the edge of the flank has to hit you. So that was the idea behind this, and that's the idea behind this plot, okay? And again, I'll go into it again. I'll let that kind of sit in your head a little bit, and then I'll go to a visual aid that will help. So 0 degrees is aimed at you. I'm firing a CME right at you, okay? Big solar storm right at you. 10 degrees off, right? I'm going to be 10 degrees this way or 10 degrees this way. So I'm not firing it at you. I'm kind of firing it off to the left or to the right, east or the west. And as you get up to 30, 35 or so degrees, well, now I'm over here or over here. I'm further, my gun is not aimed directly at you, right? Here's my gun. Here's 0 degrees, here's 10, here's 20, here's 30, ish like that, right? Or 10, 20, 30 degrees. See what I'm saying? So my gun is not firing at you as you go further off on this axis, okay? So that's the first thing, is just recognize that that's what that is. So the gun firing at you is here, the gun firing not at you is over here, okay? Further and further away. Bad aim. So it's, in a sense, it's kind of like an aim, right? How well is the sun aiming at you? And then up here is the transit time, okay? So you've got hours. Here's 14 hours, 16, 18, 20, 22. So that's what they're plotting, which is not necessarily, intuitive, but okay. And then they've got all sorts of dots. See all the dots? Okay. And they seem to kind of fall into 3 classes. Well, sort of. This is the only statistic, so and we'll talk about why there's a line with only 1 dot in a minute. But you notice, especially with these two, there's kind of like 2 sets of events. So you see an event here, an event here, an event here, an event here. What these are, as you can see the dates, these are all extremely fast events. Okay, that is the fastest on record. And as you can see, their time of arrival here is 19 hours. You can just slide over here. Here's like 20, a little over 20 hours. Here's just under 20. Here's about 20, almost 21. Here's 21 and an ish, give or take an ish, see, coming up to 22. So here's around anywhere between 19 and 20 some odd hours, okay? And notice that they kind of all fall on this, if you do a linear least squares fit, you kind of get this just for this grouping of. And then, believe it or not, there's another set that's over here. And these are all below about 15 hours. No, sorry, all below 18, 19 hours. So so you can see this here, this is about, 18, this is maybe 18 and a half, this one's 17, 17, right? These guys seem to fall on a similar line. And so they started noticing a pattern that, whoa, there's a grouping that's up here, there's a grouping here, and what that means, and why are they scattered on this diagram? Well, because they're scattered by how well did the sun aim. So here's one that was aimed reasonably well. It was only about 7 degrees off center, so my gun's right there, almost at you, right? But here's one over here where the gun is like 35 degrees off, okay? Because you have to take that into account, right? You can say, how long did it take for this event to hit Earth? Sure, that's great, that's fine. But was the gun aimed at you? How well was the gun aimed at you? Well, you got to take that into account, and that's what causes the spread here. So the interesting thing is that when you start doing this type of plot, then it doesn't even matter necessarily. If you start getting a trend, then it doesn't even matter really where the gun was aimed within this range, because you can always extrapolate what it would have been like if the gun was aimed at 0 degrees, right at you. And that's what this line does, is it takes all of these events that are on this, that are kind of following this trend, and it says, well, where would these events, how long would the events have taken if they were actually fired right at us? You extrapolate down to 0 degrees, down here. This is where the gun was aimed at us. So for this class of events, if they had been aimed perfectly, it would have been about 19 hours. Does that make sense? Hopefully everybody understands that. So that includes the Halloween storms. We had 2 in October 2003. You guys remember that? Those are probably the biggest. We had one in 1989. That was also the same year. It wasn't the 1989, the superstorm that we had March 11th or 15th, I forget. That caused the Hydro-Quebec grid default to close. But we had one the same year, believe it or not, that was faster. The Hydro-Quebec, the 1989 event, doesn't even fit on this curve. It's not even here. Not that I can tell. No, it's not even here. Okay? So we actually had one later that year that was actually faster. But we don't even know that it existed, do we? October 1989, do you hear anybody talk about it? Why not? Should be bigger than the 1989 storm that everybody knows about, that didn't even make the grade to be on this thing. Why is that? It was a bigger storm? Maybe, right? Start seeing how things can be a little bit squishy when it comes to trying to define things from a quantitative point of view. Storms that you think are huge may not be so huge in certain characteristics. Storms that you think that you may never even heard of can actually make the grade for a Carrington class event or near Carrington class event, fast event. In fact, where's our 1859 event? Is it the fastest on record? Not by a long shot. Why? Because we have this down here. There was an event that was much, much faster. Okay. Now, getting back to this, the Carrington class event, which is this 1859, right? September, everybody probably knows this by heart. You'd think it's the fastest on record, and you think it's the biggest, baddest boy that's out there. Well, maybe not. Okay. It hit us in about 17 hours. Now, granted, as you can see, by it not being aligned on this axis over here, right? It's not over here. It's over here, which means, whoops, pardon me, right here. If I track this thing down, right? It was shot about 25 degrees, well, 22 or 23 degrees off axis. Whoa, did you guys know that? The gun wasn't aimed at Earth. It was aimed over here, or over here. I forget which side. Was it east or west? Anybody know? Which side of Central Meridian was it? I can't remember anymore. I've looked at it so many times and I did not register. I did not remember. So either here or here, right? But not on axis. I know, laughing. How could I forget such a detail? Well, you know, it's a long time ago. My memory ain't all that good. You know, 1859, I've been around a long time, but no, I'm kidding. Anyway, here's the cool thing. With the grouping of events that were in this very fast class, right, faster than even the Halloween storms, right? We're talking about events that got to Earth less than 19 hours. If you track that back to if the gun had been aimed at Earth, directly at Earth, you'd get just under 16 hours. Okay. So you could think, well, it is the fastest on record, it's just that the gun wasn't aimed at Earth, it was aimed over here or over here. No, not true. Because even if you track that back to 16 hours, even if you take that gun and swivel it back so that it's pointing straight at you, straight at Earth, right, which is what this line does, it's still 16 hours, which is more than this event. This event still, even when the gun wasn't aimed directly at Earth, still got to Earth faster than the Carrington-class event, than the famous Carrington-class event would have if it had been aimed perfectly at Earth. This means this is not the fastest ever recorded. Okay? North by northwest, thanks. If that's a place where it was. Okay, so up here. So the gun was aimed this way. Okay, if that's what that was referring to. Thanks, Robert. Okay, so let's, for just a moment, let's just talk about this event, the 1972 event. Anybody recognize this event? Notice the date. Okay, this is during the Apollo era, when Apollo was active. Okay, now granted, we didn't have any missions on the moon at the time, thank goodness, and we will talk about this event. We will return to this event later, I promise you, because it's a very important event. But we're not probably, I don't know if we'll get to it today. We'll see. If we can, that'd be great. But if you take this event, so what they did is they had this line, right? They see this trend, and they noticed the same slope really was a linear least squares fit, really fit these events as well. And they're like, whoa, huh, okay, that's good. I mean, we've got repeatability here. So we've got this event that doesn't fit any of these, right? It's a big outlier. Well, maybe just like these seem to be kind of a subclass and these seem to be kind of a subclass, maybe this is another subclass, faster subclass. So even though we only have one, right, because, I mean, think about it. Space age hasn't been around for very long. Kind of hard to get really good data. We've only had telescope, ground-based telescopes since about the 1750s. We started really looking at the sun, paying attention, getting an idea that space weather even exists, to a point where we could actually try to quantify things. You know, Carrington back in 1859, that was the first time that we ever had a flare recorded. So we weren't even really understanding of space weather and how it worked until maybe around here. So it's really hard. That doesn't give us much time, especially on the time scale of the sun, to really get a lot of really, really, really big events. So, you know, this is kind of what we have to work with. So for this super fast class, we only have one event, right? 1972. But since we already had these two lines that were reasonably repeatable, let's just suppose that the same thing exists for this class. So in other words, if the 1972 event, which was actually fired about 12 degrees, or no, 16 degrees or so off of the Earth's sun line, right, which I shouldn't say east or west, it was, you know, like this in a cone. So it could be north, south, east, or west, but not aimed at you, right? So, you know, he's a drunken sailor, like I often call the sun, right? Oftentimes not knowing where to put the gun, just not ever getting it right at you. So about 12 degrees off Earth's sun line. But if we assume the same kind of rule applies, and we apply that same line, even though we only have one point here, it's speculative, okay, fine. But let's just see, right? We have reason to believe that perhaps this is a valid speculation. There's some quantitative basis for it. So let's just see. So if we take that and we extrapolate back to 0, so now the drunken sailor becomes a sniper. And for that event, When would it hit Earth? Good night. In just over 12 hours. So if the 1972 event, okay, forget 17 hours. Everybody says, oh, we have 17 to 19 hours before it hits us. Stop using that. The sun can fire them faster, guys. And if they fire them like a sniper instead of a drunken sailor, 12 hours. Okay? But again, how many people even recognize that the 1972 event existed? Or how about the 1967 event? You guys even remember those? We'll talk about them. But notice the 1989 event, that's pretty much everybody knows, that's the second most famous event. It's not even on this list. How does that work? How is it that one of the most impactful events, what we call our standard candle nowadays, the 1989 event, how is it that's not a Carrington-class event? It wasn't. But it did so much more damage than potentially all of these Carrington-class events. Maybe because it's not so easy to define them. Maybe because technology is changing. Yeah. So to kind of help put that together, boy, that thing moves slowly. Oh well. To help put that together, what I want to show you is, and I'm not going to show the plot. There's a plot in this paper that actually kind of tries to show this same kind of thing that we're going to see. I'm sorry this moves so slowly. I just grabbed this off of one of NASA's blogs. You'll see a big CME not going toward Earth, but you'll see that the extent of this thing. See, so this would be 0 degrees, right? This would be maybe 20 degrees this way or 20 degrees this way. So if the gun, so you can see that if the gun is firing a CME straight out this way, you don't have to be exactly dead on for that CME to hit you. There is a spread, right? And some CMEs can be massive with big Carrington-class events, which I didn't put on here because I couldn't quickly find one. Those events can be massively spread in longitude. So you don't necessarily have to have a CME hit you dead on, like you see with this thing, right? So that would be 0 degrees. So if a gun, you know, if the sun decides to be a drunken sailor and decides to aim off of center, well, you'll still get clipped by it because these things are so big. And that's why a plot like this is actually workable. Okay? Why you can actually have something that's off 30 plus or more degrees. And likely there are events that, you know, obviously that can go even further than that. But the thing is, once the events get beyond about 30 or 40 degrees, right, and you're just getting the flank of them, are they Carrington-class anymore? At Earth? No. Because you're getting the fringe, you're getting the edge effects of these things. You're getting just the fringe of this, right? So you could have a Carrington-class be launched kind of off, you know, off axis, and it can still hit Earth. But at Earth, it's not a Carrington-class. Perfect example of that is September of 2017. We had back on September 10th, we had an X 8.2 flare that was occulted. That was the second largest flare of solar cycle 24. That was either a Carrington-class or a near Carrington-class event. It would rank in here likely. The problem is we didn't have a spacecraft that really could catch it at its apex. It was shot, and I've said this so many times, it was like a bullet being fired here, okay? So we're not talking 10, 20, 30 degrees. We're talking almost 180 degrees. Well, probably more like 95, maybe 100 degrees away from you, right? Bam! This thing was so massive that the flank of it still hit Earth and caused a G1 level storm for 6 hours. As soon as it hit us, it was like a brick wall. And it was the flank of this thing that did it. And I was like, oh my gosh, this thing's intense. It was the craziest thing I'd ever seen. And luckily, we just passed through it in 6 hours. We were out of it because it was just the hairy edge of it. And the fact that it slammed us to a G1 so quickly and so hard, and it was so intense, even at just the flank of it, I was just like, thank God we didn't get hit. It hit Stereo B, but Stereo B was already dead by that time. So there really wasn't a big hoopla about it, and a lot of people to this day don't even pay attention to it. I do, though, because it was a massive event. And the idea that something that shot 100 degrees away from you could still instantly cause the impact that it caused shows me that I wouldn't have wanted to be in. That is probably the closest I think I have ever come, if anyone asks me. That was the closest that I had ever come to being like saying, wow, if that thing, because if that thing had been aimed straight at us, I would be, guys, we need to turn down our power. We need to roll back some of the work, we need to just really kind of batten our hatches. Everybody get to know where your amateur radio operators are, find out who has solar panels on their houses. Just kind of get ready, because that was going to be a big one, had it hit Earth. So has there been a time when I've actually been a little bit nervous? Yes and no. It was one where I wasn't nervous because it was shot so far away from us, but it sure opened my eyes that, okay, we need to take this stuff seriously when it comes to these big events. So have we seen Carrington-class events in our lifetime? Yes, absolutely. And probably more recently than you think. But just like the drunken sailor the sun is, oftentimes the aim is pretty bad, or it's really bad. Okay. And so it makes it harder to get these big events hitting Earth. So hopefully this gives you some idea of the framing here. So this is a very quantitative look at just one aspect. Let me see what I was going to go to next. Just one aspect of how to quantitatively define a Carrington-class event. And already we find that, yes, our classic 1859 event makes the grade, but it isn't the fastest. It's not number one. So I'm sure that's already going to upset people. And even if we put it back to a sniper's shot instead of a drunken sailor shot by the sun, it's still not faster than this one. And this one wasn't even a direct shot either. A little bit better, right? Instead of 25 degrees off, it was, 16, 17. But it still wasn't sniper. Okay. So let's talk a little bit more about how that analysis was done, and how do we know even that was true? Well, it's actually pretty easy. Even way back in 1859, it's actually quite easy. And this is one of the reasons why Carrington-class events are so loved by the scientific community, because they're so easy to spot. They're easy to spot even in our magnetometer records. They're easy to spot from flare, from cradle to grave. Why? Because of magnetic crochets. Okay, and I'll show you the actual magnetometer reading. This is kind of a redo. Cliver and Svalgaard, Ed and Leif did a really good job with this paper, and they've actually written several papers that I really love on the Carrington-class event, doing reanalysis and data forensics, with modern eyes on what space weather phenomenon, what coronal mass ejections and solar flares, and what their particular phenomena are, and how the physics of it evolves. You can always go back and look at older data and then think about how to reverse engineer the details that are missing, right? Because we didn't have the type of instrumentation back then that we would have needed to really do a modern analysis of it. So what's neat about, and I'm not going to go into detail of what a magnetic crochet is, but in a nutshell, amateur radio operators probably recognize it very easily. You can have a solar flare that is so intense with EUV and X-ray flux that it actually, as it occurs, it actually causes an ionospheric disturbance. It actually causes what we call an SID, a sudden ionospheric disturbance, a SID. And these ionospheric disturbances, literally, because of the ionization, they cause these spot ionization on the day side of Earth. That ionization literally causes enough potential to change the Earth's magnetic field. right, at that spot, okay, at that localized area. So a magnetic crochet, for instance, is not seen on the night side because that's not where the solar flare is altering the ionosphere. You know, to be honest, HAARP is nothing on this. Okay, so anybody who thinks HAARP is like this granddaddy crazy thing that's just going to rip the ionosphere to shreds and the military is, you know, using it to control everybody's minds, I don't think the HAARP even has a chance of making a crochet like this, or a crochet at all. Okay, but a solar flare, a big solar flare can. So this is actually when that Carrington class solar flare, the one that Carrington drew, this is when that thing happened. So this was the jet engine that fired off underneath that coronal mass ejection that propelled it forward. Okay, it literally, because of the solar flare signature in X-ray and EUV, altered the ionosphere enough that we could actually read it on magnetometers on the ground. Okay, so that happened at this point, between 11 and 12 on September 1st. As we move out, you can see here's midnight on September 1st. So now we're into September 2nd. And this right here, whoosh, as it goes off scale this way, is the horizontal component of Earth's magnetic field. Well, this whole thing is the horizontal component of the Earth's magnetic field. But it goes off scale. Okay, and we have to reconstruct kind of what it is. In this case, it's called horizontal force, just for those of you who are, you know, study this. The old-fashioned way of saying a nanotesla is gamma. So that's why you see gammas. Okay, so this is nanotesla. We don't use gamma anymore, but historically, that's what we do. And horizontal forces, it's moving in a particular direction. Don't worry about the fact that this is going this way as opposed to this way. It's just saying horizontal force. I'm not going to get into the details as to why. It's still a force, but it's a negative force, which just means a direction. Which direction are you going? Okay, because this is a vector. So, and people, you know, scientists care right now, but for what we care about is really just the timing. So as you can see, sometime after 11, right, before 11:30 to midnight, it's 12 and a half hours. And then we hit the impact here, another 5. Okay, so about 17-ish, 18 hours. That's how we get travel time. So those of you who are wondering how in the hell do we do that if we didn't really see or we don't have a good idea, it's still right there in the record, right? You don't have to go and look at Carrington's drawing, their diagram of it, this, and get his timing there. We actually have it in the academic record, okay? And it literally is rate times time equals distance. Funny thing is, let me stand on this side for a second. Scientists still decide that they want to redo things. So here it is in the Cliver paper. Here it is in the Russell et al. Paper. Notice they now have reversed it because we're so used to looking at dips as opposed to peaks. Like with DST, when it comes to magnetometers, we like looking at dips a lot of the time. So as you can see now, and I just did this for fun, now instead of having it be horizontal force this way and it's rise, now it's horizontal force this way. It no longer says gammas, it says nanotesla. And the peaks are dips, okay? And this is still same plot, they just flipped it over. Convention. Convention changes over time. And you're going to start seeing that. And I'm setting the stage here. I'm not just showing this for fun. I'm setting the stage here to let you know convention changes over time. We measure things differently. We look at things differently. We find better measures of things, and our technology changes, okay? Which is going to become very important here soon. So this and this are the same plot, right? Here's the Carrington class diagram here. Here's in Bombay. This is Mumbai. Right, this is the magnetometer in India measuring the same thing that was measured at Greenwich. So here's this is, excuse me, don't know why I have a frog in my throat today. One of the reasons why Russell et al. Flipped this over is to measure it with and compare it directly with magnetometer measurements that are made, that we plot today, and we always plot them as dips. Here's the Bombay measurement, so now you can directly see, it just feels better. And you can see that same dip. So not only did we get it at high latitudes at Greenwich, but we got it clear down to India. Obviously the dip isn't quite as big, but it's still a sizable dip. So this was definitely a global event. But again, as I said before, not the fastest. Second fastest, it gets the silver medal. Look how many references, right? Lots of references. But it doesn't get the gold. Okay. Transit time of 14.5 hours or 14.6. And a few things have been done on the 1972 event because it's also, mainly because it was Apollo era. Okay. And we'll talk about more about why in a minute, in a little while actually. But look at all these other events. All very fast, right? So most people think, okay, if it gets to Earth in less than a day, right, irrespective of whether it's a drunken sailor or a sniper fire by the sun, if it gets to Earth in less than a day, that's Carrington. Look at them all. Would you have imagined this many Carrington-class events or near Carrington-class events have hit Earth? Probably not, right? Since 1859? Most people think this is the only event that has ever happened. But guess what, guys? We deal with it quite a bit, quite frequently. Okay? Carrington-class events are not, although they're not commonplace, they're not as rare as you might think. And also, again, these are the ones that actually managed to hit Earth. What about all the ones that grazed Earth and therefore didn't muster up to the level of a Carrington-class event, even though they probably were? These are just the ones that are aimed close enough to Earth to have a massive impact on Earth and be fast enough to make the grade. Okay. Is this changing your mentality? Is it changing your idea of maybe how to define Carrington-class events and how often they occur? Right? When we start getting a bit more of a rigorous definition? Because to most people, all of these would be kill shots. But most of the time, we don't even recognize that they hit us. There's a few that are super impactful, right? Because we had a lot of technology at the time, or we had a lot of instrumentation up, or it just happened to be the right thing, or there was something in particular about that event that made it stand out. But it may not even have been the travel time. As we'll see with some other events that didn't even make this list. They're still called massive events, and they still had incredible impacts. They just weren't, by this metric, a Carrington class. Okay, good. So I'm gonna, let me see, where am I here? Okay, and that's kind of what I started to go on. I forgot that I put a chart. Remember, I made these charts last night, so I forgot. I put this in. I could have talked about this. So how do we define a Carrington-class event, right? The definition thus far, this is kind of a reminder, the definition thus far that we've gone over only addresses the eruptive phenomena, right? Meaning the CME, the ICME, and specifically the speed of the CME and how fast these ICMEs, and the fact that fast ICMEs can have large impacts at Earth. Because you can get a Carrington-class event just thinking about what type of impact, especially if you're concerned with the grids, right? So let's cross off eruptive signatures. We did that. That works. Okay, but what about all this? Remember, this had nothing, did you see X-class anywhere in that last analysis? Not at all, right? Because it didn't matter. It wasn't X-class anything. I don't want to hear X-class CME. It doesn't exist, right? Fast transit time, sure, right? And then you can get into the geomagnetic storm side, which is the G class of things, right? G1, G2, G3, G4, G5, right? A CME Carrington class event rated by the CME, ICME side of things will be a G5, of course, G5 off scale, right? But that's only one property. Well, what about solar flares or particulate radiation, right? Or effects at Earth, right? This was from slide 3. Well, let's get into that a little bit. But before we do, we'll take a closer look at the Carrington event. Okay. And I'll pause here before I jump into the details of the Carrington class event so we can look at those parts of the 1859 event, since it didn't win the gold medal when it came to running the race, right? Let's see if it won any gold medals anywhere else. Okay, any, someone's got a cat. The cat wants to learn space weather. That's cool. Is this making sense thus far? Are you guys enjoying how this is working? Hopefully. I see I've always learned something in these mini courses. That's wonderful. Thank you, MDK2. Hopefully nothing is confusing thus far. Half the Carrington could wipe out the grids maybe. Well, we got to keep looking at what we define as a Carrington class event. Okay. Yes, okay, good. People are enjoying the live. Thank you so much. I appreciate that. That's Bowman, the bird. Yes, Troy, thank you, Troy. Matthew Shipley, absolutely. You are a fountain of knowledge and very much appreciated. Oh, thanks, Matthew. You're always so kind. I appreciate that. I remember NOAA having scales higher than the G scales, but they retired them. Yeah, I mean, it's because we have KP, we don't necessarily need a G anything. And G5s are rare enough that it's hard to it's hard to bother with anything with a higher than a G5. You just won't. They're just rare enough that you don't even use them. So I'm sure that's why they retired them. So yes, are the slides going to be posted somewhere? No, I do not post these slides anywhere. Heck no, I have enough problems with people trying to swipe them as it is. I do not like the reason why is that if you want to teach this stuff to other people, fine, come ping me and we'll talk. But this stuff is non-trivial to teach, and so unless I understand what you're teaching and how you're using these types of slides, I don't give them out. Because I've seen people teach this stuff wrong, and it's unfair to their students as well as unfair to them. So, this does not, I'm barely qualified to teach some of this stuff when I get into different areas, because you can get a PhD in all of these areas. So just understand that no hydro flares are in that list. It's hard enough to teach this stuff as it is with all of the different PhD disciplines that are involved. And I try to be very humble about that if I'm getting out of my depth, I'll let you know. And so looking at it from that point of view, people can get wrapped around a telephone pole really easily and conflate different things that shouldn't be conflated. So I don't condone it. You've busted 2 myths, Calvin. You've busted 2 myths, I've been told, from when I was a kid. Good. Already busted 2 myths. Excellent. Wonderful. This is what I want to do. Thought Carrington was a direct hit. No. As a matter of fact, we've never had a direct hit from that perspective. Oh, that's great. I'm so glad. I'm so glad this is helping, guys. We are safe. Well, it's like saying, are we safe from a hurricane? Well, we are today. Right? But we have to look at this. It's weather. That's all this is. And so can weather be extremely menacing? Yes, it can. Are there catastrophic events? Yes, there are. Do they happen every day? Is every rainstorm a hurricane? No, it's not. Right? And that's the whole thing. Is every Carrington class event a planet killer? No, it isn't. That's what I'm trying to get at. And you'll see what I'm talking about as we go on. The Victorian telegraph system needed batteries to run. Well, that's interesting. Is that what they used to I always wondered how they powered that stuff. It tells you it didn't run on, very, very much juice, did it? No wonder we could get sparks during the 1859 event, and others. We've had issues. Great Whale event is another one. Do you think it would stop Carrington events if all the countries on the planet helped to build Faraday cages? No, good Lord, no. No, but it would help if they actually included the masses in sharing the burden of load. So, for instance, power grids have issues with rolling blackouts and things and having enough reactive power. And if you've watched the last couple courses that I've done, the one of the effects on the ground, when I get into that in detail, we go into that in detail, what reactive power is and how it can gobble up the entire power grid. It basically, uses up all of the available storage space and squeezes out the ability to deliver true power. And that's when you kind of need to make room in these grids. It's very non-intuitive how grids work. And if they solicited the public's help in dialing back their power usage during these peak times, I think we could do an amazing job of protecting the grids, because you can just offload some of this free energy that we're getting from our Earth, and take some of the load off, and allow the engineers to intelligently switch power, because they have more play in their grid to be able to offload some of the energy and keep their transformers from, overheating. We just need to we need to be more understanding of their needs, and that would help. They could disconnect the batteries when the system was running. Yeah. I know, and we'll talk a little bit about that. Telcos use big batteries. Oh, that's interesting, Chris. Thank you. Okay, guys, so good. Miyake events. Yeah, that's a different subject. That's probably going to be a different mini course. Miyake events are really cool, but I don't know how I'm going to. I won't talk about that today. There's going to be a couple events where I might actually talk about that, but I doubt I'll talk about it today. Let's see. Okay, I think hopefully I got. Yeah, it looks like I got through everybody's questions and things. Okay, good. I'm so glad that you guys are enjoying this. And yes, for those who really want to understand how the power grid works, and at least at the conceptual level, right? I mean, you can always dive deeper. Go to my, what is it called? The e-courses, I believe. E for Earth. Go to the e-courses, and I really dive into not just the indices, but also the impacts to the geoelectric grid. And you'll learn a lot about how the power grid works, why you can't just turn it off during a big geomagnetic storm. That's like the worst thing ever. That will cause a cascade. You start shutting things down. In fact, that's what happened in 1989, because they didn't know that they needed to turn off all those protective relay circuits. And so the grid automatically, when it got these overloads, it just thought, oh, mine's the only substation that's getting that overload. Let me just take it offline. And then all the substations started going offline, which then caused a ton of reactive power to get lost. And so it just put a huge load on the rest of the grid. And so cascade failure, boom, 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 boom. So turning off the grid is the wrong thing to do. But you learn about that when I go into the e-courses. So take a look at that. Okay, so let's jump into. Thank you, Matthew. I strongly recommend all of Dr. Scove's courses. Yeah, and if you go, thanks, Matthew. That reminds me. If you go to my webpage, you'll see. I think I said mini course curriculum. And thanks to everybody in the Patreon family, they helped advocate for this. I actually put up a course curriculum, so for both Space Weather Basics and the advanced stuff, the Second Chef. So you can actually watch a short video that talks about what's in each course and what order you should take them depending upon what you're interested in. And that will kind of make it easier for you to understand, because there are so many courses now, right? You can actually take something like 30 different courses. It's pretty insane. And each course is about 3 hours long, like today will be, because it's meant to be taken in a single month. That's really, you take it in kind of pieces. That's why I pause like this, so that we can just kind of, everybody stretch, take your, go get a drink of water, go to the bathroom, I answer questions, and then we jump into the next phase. So definitely take these courses, piecewise. Okay. And with that, I'll take another sip, and we'll jump into a closer look at the Carrington event, where we're going to actually try our best, with the help of some very savvy scientists, to kind of reconstruct some of these things that were not necessarily observable way back when. So the first thing you've got to remember is that in 1859, sorry, I'm dyslexic. I have a tendency to switch numbers around. If you look at the 1859 event, right, this is long before the space age. This is Victorian era, as people have already mentioned. And we had ground-based telescopes. We had been having them for, about 100 years by this time. But we had no space assets, and we couldn't get above the atmospheric window. Okay, remember, our atmosphere shields us from a bunch of stuff, right? Gamma rays, X-rays, extreme ultraviolet, right? All of these very, very high energy photons, light, that would just fry the crap out of us if it came all the way down. And so because of that, for the most part, you never see flares with your naked eye, right? That's why when you look up at the sky and you look at the sun, if you have the right filters, obviously not with your naked eyes, but you see just a disk, right? You see a yellow ball with maybe some sunspots on it, maybe some prominences off on the edge. You don't see the solar corona. You can't. You can only see that once you get above. No instrument down on Earth can see the solar corona other than in white light, which you have to use like an occulting disc, right? That's how when you get an eclipse, for instance, you can see that. But you can't really see the corona in higher energies because they don't make it through. They don't penetrate. They're absorbed in the atmosphere, or by our atmosphere, and so you don't typically see solar flares. That's why when we came to the space age and we had assets out there and we started realizing we need to look at the solar disk instead of just the corona. In fact, if you go back to my early courses, you can actually see how our evolution of instruments began and how we didn't even know to look at the solar disk first. We knew to look at the corona first because we'd never seen any like the corona in any way, or knew that we could actually see certain things on the disk. We thought we could see, just what we saw on the ground. But when we started getting space assets out there that actually had EUV, this is extreme ultraviolet, and X-ray imagery, suddenly a whole world opened up to us. And for the first time, we saw flares like all the time. It was like, oh my gosh, what are these little ribbon things going on? Well, every now and again you get an extreme event where you can see the ribbons on the ground because they're white light flares, because they're so energetic that not only do they emit in X-ray and EUV, they emit in the visible range, right? Those are really energetic. So every now and again, if you're an amateur astronomer, you might get a chance to actually see a big flare. Well, that's what happened in 1859. Remember, it only took us 100 years. And here's the ugly sunspot grouping. Now again, this is from the ground, so we don't know the magnetic polarity per se of all of these sunspots, but this was the cluster that Carrington saw. And there was actually a different, and I really should mention who it was who also took note of this event, or not event, but took note of this sunspot cluster, and actually should share the Carrington event as being something, because he wrote in his logbook, he wrote down this event occurring. The reason why Carrington gets the name and wins the prize of having the class named after him is because he's the only one who drew the picture. And he actually drew the white ribbons, as you can see. Okay, so these are the two flare ribbons that he saw in white light connecting these two regions. Obviously, this is probably a neutral line right through the center here, or it's like right through here. And these two are opposite polarities, right, likely coming together. And so you end up having a flare. Wait, no, that would be the ribbons this way. Yeah, I don't know. I have to think about that. Which way is the neutral line? Hard to say. It's hard to say exactly, but you see the train tracks here, so maybe not. Maybe it'd be this. Anyway, the neutral line may have been this way. So at any rate, with the two ribbons here like this, being in white light, they didn't last all that long, but it gave him a long enough exposure for him to be able to gave him a long enough views for him to be able to draw these pictures and map it out. Okay, and that was on September 1st of 1859. Okay. Now, regarding this particular event, it was the largest in the last 500 years. It's estimated to be about 3 times larger than the March 1989 event, which is the one that took out the Hydro-Quebec grid, right, and shut down, the James Bay network. Some reanalysis indicates that maybe it's only 2 times bigger. Yeah, there's still, because you have to do forensics. It's kind of hard to tell. And Cliver et al. Are the ones that talked a little bit about that. So I'll show you their paper in a minute. Another paper that they did. It's obviously, as we've talked about ad infinitum, the most well-recognized space weather event in history, and it became the benchmark for a whole class of extreme events and cultural panic, right? But the funny thing is, it wasn't just one event. It was a series of events that occurred over several days in late August through early September. And that's one of the things that people need to understand, is that a lot of times the Carrington-class events, as defined by their impacts at Earth, oftentimes are 1-2 punches, okay? Because as we've talked about and we've learned from space weather courses, we talk about these bad actors. When you get a bad sunspot cluster on the sun, and it's just firing stuff all the time, it continues to fire stuff the entire time it's on the Earth-facing disk, from the time that it rises on the east limb, rotates across the disk, and goes off to the west and disappears behind the sun's far side, right? And so you will not just get one single event. You will get solar flare and radiation storm and CME, and then another flare and another radiation storm and another CME, and boom, 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 boom. And so they oftentimes will not just be isolated single events. So here's the paper that one of the papers. Yeah, this is it. This is the Ed Cliver paper that has been done. It's also open access. I always try to find papers for you that are open access so that you can find them. This is the space weather. Sometimes I can't. Sometimes I have to go into my archives. But usually I look for ones that have maybe an ARXIV or just some open access journal that you can go to look in more detail, because I want you to hear it from the horse's mouth if you're willing to read the articles. But another, again, 1859 event is just, there's just so many papers out there. And yes, some of the authors that write one paper go on to write other papers about it, because there's just so much to be able to dig into. And if we look into this particular event, now I get to actually show you the actual magnetometer data that had the magnetic crochets in there. See this? So this is the magnetometer event. I mean, one of the magnetometer traces that actually has the solar flare, the magnetic crochet. Okay, so this is a Greenwich observatory, and you've got two different tickers, tick, 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 tick. So they're little needles that are just going on a drum, right? The big drum, and the needles just sit there and go tick, 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 and read out what the magnetometer readings are. And when you get a big event, it goes off scale, right? Well, this was just the solar flare. The CME hadn't hit yet, right? And these are ticks for like hours, I think. And notice there are multiple things going on. There were multiple flares, actually. And I forget why, what did he highlight here? I forget. There's some writing here, and the writing had said, the above movement was nearly, oh, right. So this was the magnetic crochet. It says, the above movement was nearly coincidental in time with Carrington's observation of a bright eruption on the sun. That was actually written right here. You can maybe vaguely see that. So he says the above movement was nearly coincidental in time with Carrington's observation of a bright eruption on the sun discovered over a sunspot. Okay, so they recognized this and wrote it right on the drum. Pretty cool. And there's a ruler for reference, so you know how big the paper is and how far the deviation was. It was a big deviation. Okay, so they knew that this was a magnetic crochet. And this one was 12 hours off, but the same thing. So focusing on, and that's the whole point, is I want to start focusing on that solar flare. So when you have a magnetic crochet, right, you can actually start comparing it to other events. And the reason why is because, and I don't want to go into detail, so I'm kind of pausing to say how much detail do I want to give, and how much detail can I give, because this is a little bit outside of my expertise. So when you have these events that occur prior to the modern age, and yet you have lots of events that have occurred since the modern age, you begin to build up a database of proxies, Okay, so you can measure a flare directly from the X-ray flux. You can measure, or you can measure a flare indirectly from different types of fluences, TSI, total solar irradiance, bolometric fluences, for example. And you can start, you know, in ionospheric disturbances, SIDs, right? We talked about the sudden ionospheric disturbances on the crochets. You start building up kind of a proxy database. And so if you compare one metric to the other, it gives you a way to compare historical events where you may not have the direct observation, but it gives you an opportunity to compare the direct observation from modern day events to the proxy that was used, or the proxy of the observation. There are different observational methods of a solar flare that were indirect for historical events before we really knew how to directly measure something. Because you start saying, oh, well, a flare of this intensity causes this kind of magnetic crochet, right? And you go, okay, a data point. And this flare over here causes this kind of magnetic crochet. Okay, another data point. Now I can draw a line. Oh, and I got this over here and this over here. Okay, now I got 3 points. I got a better line, right? Oh, I got this one and this one. Oh, good, I got 4 points. I got a great line. I now can make a decent fit, right? And so you get an idea of where things go. Well, that's what's happening here. Okay, because what happens is that if you build up enough events of different types of flares, and you can compare the direct fluences, soft X-ray fluence in this case, to, let's say, total solar irradiance, bolometric stuff, ionospheric disturbances, right? You kind of start getting an idea of where flares of certain intensities, how much of an impact they make on TSI or SID or magnetic crochet. And so it allows you that when you come to an event where you only have the magnetic crochet data, you can now extrapolate and say, oh, that should correspond, if I follow my line, that should correspond to an X-ray flux of blah. Because you have an idea with that line that you've been building with all these things falling on it, right? You have an idea of how direct measurement of solar X-rays compares to, let's say, a bolometric fluence of total solar irradiance, okay, or an SID, or other things. And we'll talk about another thing in a minute. So when they look back and they did this analysis, they did this to try to understand from data like this, what was the X-ray flux? What class of flare was it? Well, I didn't put a circle on it. What was this? X45. Whoa! Holy crap! That's big, right? By contrast, the 2003 events, X35 maybe? Some people say X45 for the 2003, the October 2003 events. Remember that? So they're near same ballpark. Here they are right here. Here's the X35, which is the 2003 events, okay? And again, this is, it's the proxy because there's always some slop in the line, but because these flares go off scale, even the 2003 event went off scale, right? We lost it at like X17 or 18 or something like that. So they go off scale, so you always have to reverse engineer. So some people have actually reverse engineered the 2003 events to be X45. Is that arguable? Yeah, talk to them. I don't know, probably. Right? There's always There's always scientists arguing over it. But Ed and folks here, Ed and Dietrich, believe that the 2003 events were probably X35. Okay, they downgraded them. Okay, I understand. They downgrade pretty much everything here. And so the Carrington is around X45. But hey, so the Carrington class event beats out the 2003 events, but just barely. Well, the 2003 events were extremely fast, right? They were unbelievably big, right? They were just unbelievably fast and huge. Let me go back to this plot. No, they weren't. They weren't even in the same class, right? They were up here. They were slower. Still made the Carrington class event list, ish, right? They're still very extreme class or very extreme events, but they weren't, they were totally outclassed by the Carrington class event in CME speed. But for solar flares, they're number 2. Wow. Just barely outperformed. And that's arguable even. Some authors would argue, saying, no, those were X45. They were tied for the lead. Wow. Can you imagine? We lived through the October events in 2003 pretty well, right? I mean, were there lots of problems? Sure, there were lots of problems. But we survived it. And that flare, that X-class flare, was tied for the 1859, or potentially tied for the record for a flare with the 1859 event. What does that tell you? Maybe that flares aren't things you need to worry about necessarily when it comes to Earth impacts. You need to worry about them, sure, when it comes to radio bursts. You need to worry about them in terms of, are they going to impact radio communications at that moment? Yeah, we had lots of issues when it came to those particularly set of Halloween storms. You can go look at them up, and we'll talk about them later, probably in one of the subsequent courses in this series. Especially if the Patreon community wants me to use them, because as you can see, there's lots of different events we can talk about. And so if that makes the grade and everybody wants that, then we'll talk about and we'll go into in depth of the Halloween storms. But I bet you never expected that they were basically tied. So I don't want to hear X-class CME. We have a Carrington-class X-class CME, because X-class doesn't refer to that. X-class is only a flare. Okay? Does it indicate? It indicates a ton of energy, sure, being launched. And it probably has impacts regarding the intensity of the radiation storm. But we're not talking about that. We're just talking about the solar flare. And radiation storms also aren't measured by X-class, M-class. These are just flares, guys. These are just lights. Lights and radio bursts. Okay? How loud is the sun screaming? So it turns out that the 2003 events, which were much, much slower, the sun, during those events, the sun was screaming almost as loud as it was screaming for the X45. Now, what about the 1972 event? Well, it was big, but I don't think it was this big. I forget how big it was. I forget where that event is on here. But it wasn't, I think it was one of the it might have been one of the X17s. But it wasn't an X45, and it wasn't even an X35. Okay, those were much larger. And yet the 1972 event takes the cake for the speed. How fast does it reach Earth? You're beginning to understand that the metrics are kind of, I don't want to say all over the place, but when you've seen one Carrington-class event, you've seen one Carrington-class event. You've not seen the whole set of them. It's because it depends upon how you define it, right? So let's look, and another way, by the way, another way of looking at, and this is also from this paper, another way of looking at determining where this flare hit is by looking at the energy, or from the speed, the kinetic energy of the associated coronal mass ejection. So you can actually say, in this, at least Esmely did in this paper in 2012, determined that on average the flare bolometric energy was about 1/3 of the kinetic energy of the associated coronal mass ejection. Meaning the speed of the coronal mass ejection, right, as it moves towards Earth, you can use that as a proxy to determine what the bolometric energy is. And therefore you can also kind of get an idea of what level of flare you might have. So that's yet another proxy. Now, I haven't dug into Esmely's paper to take a look and look at this in detail, but it is definitely a possibility. And I might, if people want me to. It's just so many rabbit holes you can go down, because there's so many different ways to reanalyze. And in fact, they may be even use that for the 1972 event. I don't know. I need to go back and look in particular to see the details of this. But this was the first time I saw that being written, that you could actually use the CME speed to try to backtrack and get an idea of how big the flare must have been that, was the jet engine that propelled the thing forward. It's an interesting idea. So scientists all the time are looking for different metrics by which, and different proxies by which they can analyze and reverse engineer some of the details that in our modern age we actually take for granted when it comes to observing these big events. We should be thankful that we have so many missions that fly. Oh, I just put it later. That we have so many events that fly, or spacecraft that fly, and give us all these different ways of looking at these big events to understand their nature and how much impact they could bring for us. So there was that. Now, just so you know, and it's not really super critical for our analysis now, because we've already talked about the speed of these things. We already got the transit time, right? So we have an idea of what the speed is. But they actually, in this paper, in Ed's paper, they actually went back and they decided to look at the solar wind, try to reconstitute the solar wind. And I forget exactly what they were looking at to do this. It's assumed solar wind parameters, I think mainly from DST. They just kind of assumed this from looking at how fast the thing must have been moving, and then also the magnetometer data, how the Earth's magnetic field responded. And so they looked at maybe at the back end of this thing actually being faster than the front end, but you can see over 1,500 kilometers a second. So anytime you guys see me talking about coronal mass ejections or ICMEs, and you see me looking at solar wind data, and you see a speed that's like 500 kilometers a second, 600 kilometers a second, maybe even 700 or 800 kilometers a second, we're not talking these really, really fast events, okay? They're not kill shots, guys. And no, I'm not scared when I'm talking about these events, because we haven't had one hit Earth that's that fast. I've seen them in the record when I was a grad school student. I've seen solar wind where you had a 11 or 1,200 kilometer a second impact, and that's really impressive. But that's what I grew up on studying in grad school, was those really big events from the really big solar cycles that we stopped having, recently, and maybe now are finally getting back to. So when people say, oh, no, we're just having these big events because the Earth's magnetic field is weakening, and the events are just the same as they always were. It's just the Earth's magnetic field weakening, and so it's because, that's going to cause everything to fall apart. And no, it's not true. It's because events are getting bigger again. If we had a whole solar cycle, a whole 11 plus years, 12 years of nothing. I mean, laughable events and ugly, ratty, hot, high altitude launches, weak solar flares, just awful events. Cycle 23 and 24 were yawn-worthy to solar physicists and space physicists like myself, who cut our teeth on beautiful big magnetic clouds and massive solar flares and 1,000 kilometer a second events. I mean, even the stream interaction regions. We're used to seeing stream interactions that are, 700-800 fast solar wind, 700-800 kilometers a second, no problem. And cycle 23 and 24 were giving us 500 kilometers, 600 kilometers a second. Jeez, yawn-worthy. Sadly, that whole generation of people have grown up with just that knowledge. And so now that the sun is actually getting back to where, beginning to get back to where it used to be, people are freaking out. Oh, it's the Earth's field. This is why it's happening. No, it isn't. It's not at all. And again, another reason why I'm not scared. I've seen these events before. Trust me, we lived through them just fine. Most of you didn't even know they existed, because the Earth does a much better job than you think protecting us, right? This is why humanity has existed for as long as we have. One thing I will note on this, you can see very high densities, realistic or not, I don't know. I would think hundreds of particles per cc. Sorry, my hand was in the wrong place. Thousands, I don't know. That's awfully high. I've never seen anything like that, but again, it's hard to tell. These are assumed parameters. having a magnetic field that dips clear down into 60 nanotesla, sure, no problem. We've seen that. We've even seen that in the space age. We saw that with the 2012 event, and we've seen other events like that as well. So that's easily doable. Minus 100 nanotesla. That's easily doable. So there's lots of different parameters that you have to worry about when you're trying to reconstruct these things. Here is the DST for those who have taken the ground level courses. You guys remember DST, the Disturbance Storm Time Index, is an index that measures the ring current, right? This only happens when you get big geomagnetic storms, so storming that's happened for a long period of time really begins to rev up the ring current and get those particles, those low energy particles, which is the energy storage of the system, get that really kind of amped up and get lots of fluxes in there. Having those particles, whether they're protons or electrons, having those particles in there in the ring current, because it's a ring and they're charged particles, well, it creates a magnetic field. It induces a magnetic field. That magnetic field is induced the opposite direction of the Earth's magnetic field, so it decreases the magnetic field and causes a depression. Okay, so the overall field that's measured on the ground is this artificial depression. Okay, and so reconstructing what this would be, or looking at reconstructing what this would be, because we didn't have obviously the DST index back then in the 1850s. It was multiple people. I think Tsurutsani. Is it Tsurutsani who did it? I forget. I don't see it right there, but it was indicated to be a minus 1700 nanotesla. A big storm is minus 300. Okay, that's a big storm. So minus 17 is huge. That, again, by this paper has been downgraded to about minus 900. So still massive, 3 times bigger, okay, than a typical super solar storm like 1989. Actually, I think 1989 was bigger than that, was minus 450. Remember, we're talking about depressions, so everything is negative. So that's why they're saying between 2 and 3 times. I think the Halloween storms were minus 300 or 350. I could be wrong. But I know that just anywhere around minus 300, you're getting to a really big storm. We haven't even seen that. With the G4s that we've had, and we'll talk about that in a bit, we haven't seen minus 300. We haven't seen minus 300, I think, since the Halloween storms, as a matter of fact. Scientists, help me with olives. If anybody knows, if I'm wrong, please correct me. My memory is definitely faulty. I am not a big geomagnetic storm person. I don't keep those statistics in my head. But again, in grad school, when I was doing all my work, that was kind of a benchmark. If you got over around minus 200, you're getting into a pretty serious storm. And then when you got to minus 300, that's a superstorm, right? And then the bigger ones were even bigger than that. You start getting into the, once every 10-year storm, it's like 300. Might have been once every 10 years. So a decadal storm would be over, minus 300 or greater. And then once every, 50-year storm is like a, minus 450 or minus 500. And then once every century will be something like the Carrington class event. So whether this is minus 17 something or minus 900, it's still much, much larger than what we would classify as a superstorm. And obviously much, much, much larger than anything we've seen from cycle 23 or 24. What we've had thus far is laughable. That's why when people say, oh, Tamitha, you're scared when you're giving your forecasts. Come on, give me a break. No, I'm not. I get tired of that, as you can tell. Okay, anyway, so if you're interested in Ed's paper, please read it. It's an excellent review of this and a really thoughtful approach. And there's a lot of good work in there. Okay, so I probably should do this more often. So we looked at the solar flare signatures, right? We've looked at the eruptive signatures. Now we looked at solar flare signatures. We know it's an X45. What about SEPs? Okay, so let's go back to that same paper. And there are other papers, and Ed's paper is a good one to look at for other citations on SEPs. And I really didn't get a chance to do a lot of digging, right? But this is just a sample of what you can find out there. Okay, so this one, again, so you have, we're doing the proxies again, right? So you have solar X-ray fluence, and you have log 30 MeV, 30 megaelectrovolts greater than 30 MeV particles. Yeah, I'll talk about it. So those of you who've taken the radiation storm classes, I call it the invisible killer. This goes back to the space weather basics. I believe in that set of space weather courses, I talk about there's two different levels of calling a radiation storm, like what Noah Swipsey calls the S-level storms. To get to an S1 level, or any of the levels, you have to cross certain thresholds with two different energy ranges. Either of them, it's an either-or situation, meaning that you don't have to have both energies to cross a certain threshold in order for it to be triggered and called officially a radiation storm. You just have to have one or the other. So for an S1 storm, for example, the marker of an S1 can be if you have the 10 MeV and above fluxes reach, I think it's 100 PFU, particles per it's particle. It's a measurement of flux, of how much goes through a particular size in a particular time. That's what flux is. So it's basically having a certain number of particles pass through a detector in a certain amount of time. And if you have 100 particles pass through this detector of a particular, what we call a normalized size, and I'm not going to go through the units because it's just going to confuse you. But if the particles go through that particular detector in a particular time, in a 1 second time, then that is a radiation S1 radiation storm. However, it doesn't just have to be 10 MeV particles. You can actually have higher energy particles. In this case, a 100 MeV set of particles, what we call a harder spectrum. If you have more energetic particles in a radiation storm, that makes the spectrum harder. If you have less energetic particles, it makes the spectrum softer. So you can, that's kind of like a way that particle people actually talk about different energy, different radiation storms. Radiation storms are, like a rainbow, right? You can have a low energy side and a high energy side. And so if you tend toward the high energy side, like in a visible rainbow, you tend toward the blue side, that would be a harder spectrum. And if you tend toward the low energy side, that would be the red side, so to speak. That'd be a soft spectrum. So that's kind of the analogy I'm using, is think of it like a rainbow. Okay, so radiation storms, yeah, they're like a rainbow. So you have so it makes sense then that if you're going to have if you're going to have a rainbow when it comes to a radiation storm, well, then you don't want to just trigger off the blue color, or you just don't want to trigger off the red color, right? You want to be able to have a range, right? Because they can be very different. So that's why there's multiple triggers for radiation storms. And so when you go back here, sorry, I have no idea why I've got this today. When you go back here and you look at 30 MeV and above, they were kind of just saying, yeah, and a lot of it had to do with looking at ice cores and how nitrates and stuff get permeated by energetic particles and what can be registered in these proxies. So you had to look at kind of an energetic threshold. And the nice thing is that most likely, most of the time, these Carrington class events are going to be on the harder side. They're going to be on the blue side, so to speak, the more energetic particles. So the idea that they would have particles that are over 30 MeV, and a lot of them, is quite high. But it isn't always the case. And we'll talk about, in a minute, I'll talk about an event that is kind of an outlier because of that. So they took this 30 MeV proton fluence, and these are all events that they know. You see all the black scatter, right? And they looked at this X-ray fluence of the soft X-ray fluence of the solar flare, because oftentimes the solar flare, the intensity of the solar flare, dictates what the seed population, the energy of the seed population of radiation storms, right? The CME then, of course, accelerates those particles as it reaches Earth. If any of this is confusing, Go back and look at my radiation storm courses, and you'll see why this makes sense. But you have a solar flare that gives you a seed population, and then that seed population continues to get kind of piggybacks on the shock in front of the big solar storm, the big CME coming out, and continues to get energized. So there's a reason why you would use solar X-ray fluence, which is a flare intensity measure, and then kind of compare that to what you would expect or what you get with proton fluences, big radiation storm fluences at Earth. And so you can build up by comparing those two, saying, okay, I've got this X-ray intensity and I've got this radiation storm intensity, right? And here's another flare with a different intensity with the soft X-ray, and then this is what the proton fluence is like, right? And so you just keep building up statistics, and it's more ratty, it's harder, it's not as nice, but it's still a nice line, okay? So once again, when you have something like this, now you've got a measuring stick. And we already saw with the solar flare, they were able to get kind of an X-ray fluence, get an idea of what the fluence is. And so they have an idea that, the radiation storm for the 1859 event must have been way out here. Very high fluences, okay? Now, the problem that they have with this, and you can see the big error bars, is that there were some records that didn't agree, but it was about having energies that are even higher than this. So basically you have to, with a lot of ways that you measure by proxy the impact of radiation storms is through ice cores and other ways that particles have been bombarded by these, radioactive kind of things. And so it alters the isotope, or it changes the ratio of certain isotopes that are, in the ice or in tree rings, or, there's half a dozen different ways of looking at it. And Miyake events fall into this category. So, when we try to do forensics on Miyake events, same kind of thing. And so, there's a lot more spread. And sadly, you can go to different areas, and this site will confirm it. This site will say, no, it never happened. and so it's really tough. And so there's a lot of error in this. And there's probably a lot more argument between scientists as to where this sits. But it is quite high. Okay, so we do know that there was a very strong radiation storm. Is it the strongest radiation storm? Possibly, possibly not, but it was very high. Now, the funny thing is that the 1972 event, I don't even think there was, they couldn't, I think if I recall, they couldn't find any evidence of the 1972 event in this. So what does that mean? Does that mean it didn't have a radiation storm? No. It meant that the radiation storm was likely soft. It was on the red side of the spectrum instead of the blue, because it didn't have many high energy particles above 30 MeV. Okay, so it doesn't mean necessarily that a radiation storm didn't happen with the fastest event on record. Of course it did. Right? It just means that they were lower energy for whatever reason. And part of that I think was because the X-ray flare was like an X-17. It was smaller, and so it didn't give us that seed population that was energetic enough that it ended up being really, really high energy particles. I don't know, and I don't know if we'll ever know. But we'll look at more about the 72 event. We definitely know it had major solar radiation. There was a major solar radiation storm because of what it did to the ozone layer. And we'll talk about that when we go through that event. But nonetheless, the 1859 event is really high on the list when it comes to radiation storm. Is it the highest? I don't think so. I think there are a couple others that were higher. The paper talks about it, but it was still high enough. The problem is, again, if it were way up here at this edge, yes, it was very high. It was probably the highest. If it's down here, no, not even close, right? But it's also a matter of what was the spectrum like. And the sad thing is I don't know if we'll ever know what colors in that rainbow were. Was it almost blue, all blue shifted, or was it red shifted? And I'm not talking Doppler shift. I'm just using that as an analogy to talk about a spectrum. Energy spectrums are kind of hard to visualize, but light is easy. Rainbows are easy. So rainbows are spectrum. It's just spread out, right? The low energy stuff is the red stuff. The high energy stuff is the blue stuff, right? So you have that, and everything in between are all these different colors. those types of energy spectrums happen in particles as well. You just don't see them. But the same kind of idea works. So will we ever be able to pull out the rainbow that was the 1859? Probably not. And that therein lies why there's such a huge spread, is because it gets really, really difficult to lock down the radiation storm. It's probably the hardest metric of all to lock down, simply because it's hard to reverse engineer a rainbow. There's some words to live by. It's hard to reverse engineer a rainbow. Oh, I love mini courses because they teach me how to teach, and the weirdest stuff comes out of my mouth. I hope somebody remembers that, because that is, I'll be razzed for that forever. I'll put that on my email tagline. Okay, I'm trying to think if there's anything else I wanted to say about this. I don't think so. Hopefully that's clear. Yeah. Is that clear, guys? Law, reverse engineer. Yeah, exactly. Yeah, the banana belt of Oregon. Oh, you guys are talking. Cool, you guys are talking. Let me know if this is clear. We had a 5'6" off the coast of California. Did we just have an earthquake? Goodness. That wouldn't surprise me. We rock and roll all the time. Why can't you talk about what we do need to worry about? I am. Frequency particles, frequency solar flares that are attacking the pacemakers. Solar flares don't attack pacemakers, guys. Particles, energetic particles do, and I do talk about that. When there are solar radiation storms, I do talk about when they are happening. You need to look at it in my 5 days. I say if you're a high-risk passenger, that's people with pacemakers, that's people with electronic devices implanted in them. I will tell you, and I am talking about it, you need to worry about when the rainbow is blue, okay? Worry about the hard spectrum. And we haven't had, not even over the last cycle did we have many that had hard spectrums that were threat-worthy from that perspective. For people who are, dealing with chemotherapy and radiation treatments, sorry, couldn't think of the word, radiation treatments, the lower energy, the softer, red side of the rainbow, then that's what they can worry about. And the prenatal passengers, they can worry about the lower stuff. But people who have implanted devices and pacemakers, ICDs, those types of things, that's more the high energy stuff. So, and that doesn't happen very often. And maybe we'll start seeing it in this cycle. We've seen a few more radiation storms than we have seen, but we haven't seen really any super high energy stuff. That's not why I'm talking, that's why I haven't been talking about it. It's because it hasn't been a big deal. So, let's see. Hopefully that answered that question. Just felt an earthquake. Okay, yeah. Yeah, I thought I felt something too. But it obviously wasn't enough to cause any issues with the feed, so. It was a 5.4. Okay. Where was the epicenter? It'd be nice to know if somebody could put that up. I'm still loving the reference that Tamitha Scove gave for the amount of CMEs from the sun. I called it a jellyfish. Did I really? Oh, geez. Okay. You got to tell me, Matthew, you got to tell me offline when and where I said that. That's funny. Cell phone towers. Solar flares only, cell phone towers are only a big deal. Oh, Ferndale. Okay, thank you. Cell phone towers typically are only affected if the sun is in direct line of sight. So like if I'm the sun and I'm screaming, I have to scream straight at you. And if you're a person who's trying to get a cell phone tower that's between you and me, if I'm screaming, then that can mask your reception. If I'm directly overhead and you're looking at a cell phone tower this way, it's not a problem. So direct, line of sight communications or radio signals don't get disrupted by the sun unless the sun is basically on the horizon, either dawn or dusk, either directly at, aiming at you. So you're looking at a cell phone tower and the sun is behind you, or behind the cell phone tower and you're looking straight into the sun, or the sun could be behind you, right? So the sun could be, I could be, if I stand out of the frame and stand behind the camera, it won't make sense to you. But so in other words, near dawn or near dusk, and you're looking at a cell phone tower along that line, right? So either the sun is at your face and you're talking to a cell phone tower, or the sun is behind you and it's screaming behind you over your head. That is when radars and direct line of sight for things like cell phone towers get in trouble. Satellites, it's a little bit different, just simply because satellites have to go through the ionosphere. And so that the ionosphere can light up like a Christmas tree, and then that kind of scatters signals and makes them harder to read and harder to understand, depending upon whether it's, what frequency it's at. And then, of course, satellites are oftentimes above, and so zenith, when the sun is above your head, right, then it has a much bigger chance of blocking that light, because once again, blocking the light, blocking the signal, because not blocking it, but just overwhelming it, because it's once again a kind of a line of sight thing. So you really have to worry about when it's direct line of sight. That's what you have to worry about more than when it comes to, excuse me, take this off. Then when it comes to skywave. When I talk about amateur radio operating, skywave propagation is very different, because it's using the ionosphere as a kind of like a mirror to bounce. I shouldn't say mirror. Using the ionosphere as a way to bend and refract light back, or refract the signals back down to the ground. And so the condition of that ionosphere is really what bothers them. And so that they've got kind of like a double punch. It's not just the solar radio bursts that are a problem for them. It's also the condition of the ionosphere. So they get impacted far more than people who are looking at doing direct communications with a cell phone tower or even with satellites. But it still does happen. So hopefully that answered that. Okay. All right, so now we're going to, okay. I see a lot of rainbow jokes now. How many amps order of 1850? How many amps did the 1859 cause in the upper atmosphere? Oh, that's a good question. I don't think we know. There may be some papers that talk specifically about about that impact. I know we saw ionospheric disturbances. As a matter of fact, it might be the 1859 that caused the biggest depression. Was it that event, or was it the 67 event that caused the biggest depression in TEC? I don't know. Some of these events are running or blurring in my mind, so that's a hard one for me to answer right off the top there. Ride Fast. That's a funny name. Okay, good. I'm glad you like the answer for the cell phone towers. Whew, okay, good. All right, are very low frequencies usable during big events? Not really. VLF, they get really messed up. I mean, maybe if you're underwater, but not necessarily during big events. You get VLF waves are really messed up. They get hit pretty hard, and that's not an area that I'm really well versed in. So the specifics of it, I will not go into further, because that's definitely out of my expertise. But I do know that they are very, very sensitive to even solar flares. They can get messed up before HF, definitely. Okay. All right, good. So it looks like we kind of went through that. All right, so here becomes the interesting aspect. Now we're at the 2-hour mark. Good night. Here comes the interesting aspect that I want to go through. And this is where things kind of lighten up just a little bit, because this becomes where you kind of think more about it in the thought-provoking aspect of moving into our modern age. And what are the consequences when we start thinking about these historical events and possibly Carrington-class events moving into the future, and how our culture looks at them all. So this is from that same Ed Cliver paper. Now we've got Ed Cliver here, and then this one, I think this was also adapted, but from the different Ed Cliver paper. It might have been that. I don't think it was from the Russell et al. I think this is the other Cliver paper, but it originally was written by in Kimball in the 1960s. But I don't know if I never was able to find an open source copy of that, and maybe I just didn't look right, but I wasn't able. I again, try to stick to papers that you guys can get access to. So what I'll show here is kind of a plot of, hopefully you recognize this. This is our planet, right? A flat plot. It kind of overlaps a little. And you're looking in blue lines. These are the magnetic latitudes. Okay, so if you can see 60, 40, 20, 0. Okay. And what you're looking at here in orange are all the aurora sightings. Okay. And this was obviously during the 1859 event. We're still talking about it. And in blue, I believe, are all the magnetometers, where you had magnetometer measurements and you could see that a big dip, okay, in the magnetic field. So they're not pretty observations, but they're still observations of Earth getting hit at that latitude. So those of you who are very familiar with L shells and looking at how Earth's magnetic field works, when you dip to lower L shells, because you're getting closer and closer and closer to the Earth's, to the heart of the Earth's magnetic system, you are going from high L shells, which map to high latitudes, down to lower L shells, which map to lower latitudes, right? And eventually you get down to the Earth's magnetic equator, right? And if you were to, and that's disappearing here, and if you were to get to Earth's magnetic equator, you basically would be stripping Earth's magnetic field, peeling back the flux, not ripping it off, but peeling back the flux from the Earth's magnetic system from the day side and folding it into the night side. Okay, again, if this sounds like Swahili to you, it's simply because you haven't, you need to look at some of the mini courses, and this one was from the Earth's magnetic system, how the Earth's magnetic system works. If you want, I'll play a model. I might have to hunt for it. I didn't think about that until just now. But I could play a model run of the 1859 event so you can see how much of that magnetic field was peeled back and the flux was taken if this is the day side of Earth here. And I used to do the chicken dance. As a matter of fact, that's how you find it. Look at my mini courses and you'll see, those animated GIFs that are the thumbnails. You'll see me doing one that does this, and I go like this, and I do something like this. And so that's the chicken dance, where I'm showing how, if I'm Earth and this is the day side magnetic flux, it comes in a loop like this. When the big storm hits, it breaks open. You have a reconnection, and it takes the magnetic field, breaks it open. I connect to the solar wind, and the wind peels that flux back, and it folds over into the tail, which is now this side, okay? And then all sorts of magic happens, and a slingshot shoots particles forward. That's just how geomagnetic storms occur. But then when the storm is over, the flux folds back and reconnects. So this became the chicken dance. Okay, so you'll see that as a thumbnail, and it's very easy to spot, and it's in the M courses. And so when you peel that flux back, as you get closer and closer and closer to the Earth, okay, what we call lower L shells, you peel the outer layer just like an onion, and then there's an inner layer that's waiting, and then it gets peeled back, and then there's an inner layer from that, and it's waiting, and it gets peeled back. It's like nested slinkies. And so every time you peel a layer back, you're going to lower and lower and lower latitudes as those field lines, this is a field line that maps to Earth, as those field lines map onto the Earth's surface, okay? So that's the nature of geomagnetic storms, and that's why aurora happens way up at high latitudes most of the time, because most of these big storms are weak, and so they don't peel back very much of the flux. But when you get big storms, they really start eroding the flux, as we call it, and putting it all on the tail and to the night side of Earth. And so the auroral oval drops, it widens and gets lower and lower and lower, and the aurora comes further and further and further south, because out at the edge, out at the boundary between the solar wind and the Earth's magnetic system, the flux is being peeled back. And the thing is, eating its way in, so to speak, to our inner system. Again, magnetic field is not being created nor destroyed, it's just being folded back. It's like kind of being a person with hair in your face, right? And then you go out on the freeway and it's like, and it's all being blown back. Your hair isn't being ripped off your head, it's just being blown back, okay? But there's a very specific way that happens. And it allows, by doing that, it actually allows that auroral oval to open up and you can dissipate more energy in the upper atmosphere. Our atmosphere is used for energy dissipation of all sorts of things, which is so wonderful. It protects us so well, which is also why it's a little bit scary about colonists going to Mars, because their atmosphere, Mars's atmosphere is non-existent, essentially. It can't do what Earth's atmosphere does for us. Astronauts are hardly any better on Mars than they are on the moon, okay, with no atmosphere at all. So we have a lot to learn when it comes to dealing with space weather on planets that don't have atmospheres like as thick as Earth. Be very grateful that you breathe air and that our atmosphere is as thick as it is, because it just shields us like crazy. Okay, anyway, so as you notice, aurora sightings went all the way down, clear down to Mexico, right? And magnetometer sightings went clear down to India. Okay, you're in and that's why that one plot I showed earlier showed Bombay, right? Mumbai. Because you had magnetometer sightings, you know, where you're peeling the flux back so badly that that particular magnetic field point is wiggling and is decreasing. And so you're seeing these intensities, you know, clear down here. So that's why they haven't plotted on the same plot as showing how far down, how engulfed was at least the northern hemisphere. And the same thing happened in the southern hemisphere, because remember, you got whatever's happening in the north is also happening in the south. And so, you know, they meet in the middle. So you had aurora all the way down from the north and all the way up from the south, and you were basically getting aurora clear down to, you know, very what we call low latitudes. And here's another plot showing very similar things. But this is corrected. This is now in magnetic latitude. It's not necessarily on a globe, because it would distort the globe, because now you're dealing with these curved field lines, right? These curved latitudes, which would make if we plotted those lines straight, boy, it would make the continents look awfully weird. So we don't plot the continents. So they're talking about the latitude envelope of aurora during a time. Now this is going in time. So as you can see, there were actually two events, two impacts, one here, one here. There was a composite storm, okay, with a little break in between. And there's all sorts of ways of looking at it. There's magnetometers here, there's auroral sightings, there's telegraph stations that went offline, you know, sparking, arcing, that type of thing. And you can see the magnetic latitudes. The first impact wasn't nearly as bad as the second part of the impact. Second part of the impact brought things clear down, and here you see the Bombay magnetometer observations clear down here at about 10 degrees, magnetic latitude, okay? Really low latitude stuff. Auroral sightings were seen in Mexico, so a little bit higher latitudes around, you know, 18, 20 degrees. So, right, and that's around here, 18, 20 degrees right in here, okay. Looking at this plot, this is going to focus just on essentially on auroral observations or why did I want to show this one? Overhead, and then right. For those of you who are aurora photographers, you might appreciate this, or even just amateur, you know, people are beginning to recognize that, wow, we get to see aurora a lot. This plot is really nice because this was even back in 1859. People kept journals and were cool enough to say, okay, where is aurora? Where are we seeing aurora? People were talking about aurora being overhead. So coronas were spotted all throughout where you see the black circles. See the dark black circles? That's visual aurora overhead, coronas. So we had a massive auroral zone. I mean, it just engulfed really, like, this is why birds were singing and people were, you know, things were, people could read by the aurora. It's because it was just the band of aurora was insane. It's not like just a visible arc that was over part of the sky, or just certain people in certain areas got to see, a very small latitude range got to see coronas. People all over got to see coronas. And then you can see where people saw aurora overhead, or not overhead, but just visible aurora. So you got to see, you know, it's all over in here. And that's the open circles. So I thought that was kind of neat that that they actually had observations that distinguished things of just visible aurora and actual coronas straight overhead. And then there was one, it said the lowest geomagnetic latitude which the storm was observed was in Honolulu, at least in the United States, and that's not shown here, but it was about 20, magnetic latitude, about 20 degrees. Right. So it was a very impactful storm, right? This is a sustained G5 level storm with visible aurora seen in many, many parts of the world, especially all over the United States, right? Down to Texas, let's say. What else happened? Well, the North American telegraph systems functioned despite being unplugged, right? The worst hit operating stations sparked and burst into flame. This is, some of them burned their operators. The reason why that happened is because they'd unplug them, the things would still work, they'd be sparking, and then they caught the paper, the telegraph paper, on fire. And then that's what was burning, not the actual, you weren't melting metal. It was just burning the paper, and so people got burned as they're trying to put that out, right? Aurora was so bright, animals thought it was sunrise, birds were chirping. Auroral displays were seen as far south as we just talked about, the Caribbean, Hawaii, and reportedly Singapore. Of course, the National Academy of Sciences say that if it were happening today, it would have caused over $2 billion worth of damage. Like I said, this is why it is the most talked about space weather event of all time. And you can see there's the thing where we talked about the crochet, magnetic crochet, and then here is the event. And this is Greenwich, right? So the auroral electrojet area. Greenwich, here's where it goes off scale, and then that's on the September 1st, and then again, September 2nd, you're still dealing with it, right? So there's magnetometer goes off scale multiple times because now it's the top trace. This is actually the top trace coming back up to here. Okay, so you can see it overwrites. The bottom trace, the needles, they didn't even know the needles could bend that far. So you had these two needles just dig it across each other. I'm surprised the thing still worked if it's able to trace over itself like that. But, it obviously made the rounds, right? It made massive newspaper articles about it. Everybody's talking about, here's the Democratic Sentinel, the Brooklyn Evening Star, the Daily Courier, the Daily Progress. This is from the New York Senate or something. I can't remember what it was, like the New York Times. And you can find more articles in publication and around the internet circulating on this. People were talking about being able to read by the aurora. People were talking about, birds chirping, roosters crowing, farmers getting up and milking their cows because it was so incredible. This is the type of mass, when we read this today, this is the type of mass panic that is incited because people are thinking, buildings are going to catch on fire. The telegraph operators were burned. Therefore, entire buildings will catch on fire during the Carrington event. This is, our computers are going to fry. We got to unplug everything. We're going to spontaneously combust if we have electronics in us. Our car batteries are going to explode. I've even seen Michio Kaku talk about this in a History Channel, sadly, in a History Channel documentary that I was in. And I refused to give them the answers that they wanted. So instead, what happened is that they had Michio, who's a theoretical physicist but knows nothing about space weather, and he talked about how car batteries are going to explode. Really? Okay. I'll wait around to see that one. It ain't going to happen. I'll die before that happens, before I see that, because it isn't going to happen. You can wave a magnetic, a fridge magnet over your car battery all day long, as fast as you want, and it's not going to cause your car battery to explode. It's just silly to think that something so tiny is going to explode because of a geomagnetic storm. It's just ridiculous. But nonetheless, these are the types of panic and myth that are out there now. And why? Well, because the aurora was record-breaking, right? I mean, aurora, these are in telegraph systems going on fire and all of this stuff. This is record-breaking. Nothing else has come close, right? Not necessarily. Look at the latitudes for aurora. Once again, just in the scientific literature. 1872 event. 1872? Really? Compared to what was published back in 1859? Isn't that interesting? So in 1872, we saw a lower aurora, lower latitude. Huh. Maybe a stronger storm? Possibly. Right. Is the 1859 event there? Yeah, sure it is. Second. Right. In family with a bunch of others. And there's something else that we need to be paying attention to. So once again, not just the fact that the 1859 event takes the silver once again. The biggest event in history that's been written about by more scientists and more historians and more YouTubers and more anybody than any other event, right? Some people to the point where, to the exclusion of all others. Once again, even with Aurora, gets the silver medal. Interesting. And what does that mean, really, when we talk about Carrington-class events in general? And really when we talk about how we classify them. By eruptive signatures, by solar flare signatures, we saw 1859 didn't take the gold medal when it came to the fastest CME. 1972 did. By solar flare signatures, well, almost tied for the 2003 event, right? The Halloween events that were just recent. By particulate radiation signatures, meh, it's arguable, but wasn't the most energetic, wasn't the most blue shifted, but it was up there, right? By effects at Earth, whoa, did it take the silver medal again? Possibly, right? At least it did back then in the day. Now some of the reverse analysis that we do, maybe we see more, but at least from auroral perspectives, it didn't take it. We got a magnetometer that says, yeah, 10 degrees, but that's not an auroral sighting. Auroral sighting, the 1872 event was bigger. Have you guys even heard of the 1872 event? Yeah, I have to go back and look it up too. Right? I know it's a superstorm, but Carrington class? Interesting. So notice that suddenly, after all of this, that 1859 event, not only is it not alone, it doesn't take the gold in all of these, does it? Anyone expect that? Especially the ones that call it kill shot, micronova, all of that fun stuff. Yeah, let me see. Right? Mega flare, kill shot, micronova, power, whatever, Armageddon from God's wrath, right? All of that crazy stuff. It doesn't. So when it comes right down to it, there really isn't a single definition for a Carrington-class event, because all of these different aspects kind of seem to have a different leader or near leader, right? In fact, when we look at the space weather effects across the board, who is the winner for the SID, the sudden ionospheric disturbance? Well, the November 4th, 2003 event, one of the Halloween events, right? It's the later part of it, but it was the one that took the record. It had a biggest magnetic crochet, even bigger than the Carrington-class event. Remember, we talked about the magnetic crochet. For the solar energetic particles, well, above 30 MeV. If you're arguing that it was at the high end, then yes. If you're arguing that it was at the low end, no. But we'll give it to them. Okay? It won the gold. Let's just say. Let's be benevolent and say the 1859 event wins the gold for solar energetic particles above 30 MeV. It had a reasonably hard spectrum. Solar wind transit time, CME, ICME, 14.6 hours. You know which event that is, 1972. Right? Carrington event took the gold, or took the silver, just like it took the silver here. It took the silver here. Geomagnetic storm? Nope. Believe it or not, the Great Whaleway Storm of 1941. Okay, now, granted, this is only because We don't have DST measurements. Does the Carrington class event, even being downgraded, does it take it? Yeah, probably. Okay. But it's going to be close. And then for Aurora, which takes it? Which takes the gold? 1872. Once again, 1859 takes a silver. So here's the thing. 1859 only clearly wins gold with this event, with the solar energetic particles, if you assume that it's at the high end of that guess range. And you could argue that it takes the gold here. Okay, it is possible. But it takes at least the silver here, possibly the bronze if we want to argue that the October 2003 event was tied for the SID, the biggest flare. Okay, because this is all flare related, right, with the magnetic crochet. So we could say silver or bronze, gold, silver for speed, possibly gold, right, and silver. Would you have expected that? That we've actually had that many more events that were more impactful in these very specific quantitative measures. If the 1859 event was truly the end-all be-all, I didn't. It's like, wow. When I first read all this stuff and kind of got myself set up on it and really wanted to say, okay, how different really was the 1859 event? How much of an anomaly was it? It really wasn't. There's a lot of events like this. This is what leads people like Pete Riley back in the day to say 12% chance of a Carrington class event over the next decade. Why? There's a whole host of them. How do you classify a Carrington class? How do you declassify one that is a great winner in one area but a terrible winner in another? Is that a Carrington class event? Well, possibly. It depends upon the types of effects you're looking for or you're expecting. Right? Depends upon how it's set up. And it depends upon where's that sun aiming. Is it a drunken sailor or a sniper? Right? The reason why, if you say, well, why the hell is the Carrington class event so spoken about anyway? Why is it? Is it just luck? Well, no. And luckily there's some nice text that highlights this point. Right now, at least with the events that we've had, what makes the Carrington class event so noteworthy is that it scores high in every single category. It's in the top 3. It's on the podium, right? Maybe it's taking a bronze, but it's still on the podium. It's still medaled, right? And it does it, took the bronze here, took the gold here, took the silver here, took maybe the gold here, maybe the gold or silver here, took the silver here, right? It medaled in every category. That's why it's noteworthy. Okay. So there we go. After 150 years, the first identified space weather event continues to be one of the largest ever recorded across the activity spectrum. That's what's noteworthy about the 1859 event. Not that it's a micronova, not that it's a kill shot, whatever that means. It just means that it was a well-rounded specimen. But it doesn't mean that we haven't seen them before, time and time and time again. So when people think that I'm going to get scared because I see a big storm, you are flat out wrong. I am not frightened by these things. Earth isn't frightened by these things. And neither should you be. And that is the bottom line when it comes to the fear-mongering platform that so many people use. They are weather. We will get through them. Can they cause problems? Yes. Are we aware of these problems? Yes. Are we doing things to mitigate through them? Yes. Okay? There's only so much you can do to mitigate through them, just like there's only so much you can do about a superstorm Sandy, right? And a massive hurricane. There's no need to panic about it though, right? We live with these things as we always have, and as we will continue to do so. Now, that being said, let's get to the pop culture of this whole thing. Has anybody noticed? There's a lot of these things floating around. You notice that? Right? We have these in 1859. No. And usually I talk about these from the perspective of GPS or satellite internet or, you know, half a dozen different things. GPS for Waze or, you know, not just even your geopositioning, but for all the apps that we use. Right? But there's a really cool thing on the back if you flip them over. There's a really cool thing on the back, and some of them on the front now too. They're getting pretty good. These things, right? Do you remember when there used to just be one of them? Do you guys remember when the phones were a little tiny, or even flip phones, and they're just one little? Now there's like, you know, a whole host of different cameras all over it, right? With incredible, incredible sensitivities. And that has an impact on our entire world. And it's had a massive impact, right? You know, in pop culture, social media, everything. It's had a massive impact on how we do our lives, how we live our daily lives. But there's another thing that it impacts quite severely, and that is how we look at space weather. And I've said this before, but like I said, I've said it before from the perspective of all the technology that it brings. I'm not going to say that this time. I'm going to say that from the perspective of aurora and from the perspective of Carrington-class event signaling, right? You can already imagine where I'm going with this, right? Cell phone camera CCDs are sensitive enough to capture low-light events, including the aurora, which used to be hard to catch, right? But now we have a sea of these. These things are so much better than your eye that subvisual aurora, or aurora that you might not notice if you're not really staring, is very easily captured, and it's colorful as heck, whereas aurora to the naked eye is typically much more pale. The reason why it's pale is because our eyes are designed to see low light in nearly black and white, right? Because of the difference between rods and cones. In high light situations, our cones are activated. They're not very light sensitive, but man, they can see color. In low light, however, our cones don't do so well. So we have rods. Rods are great at picking up light, but they're not good at picking up color. That's not their job. So in low light situations, when you're looking for light and it's there, but it's dim, you're not going to see color. You're going to see the light, kind of in gray. So aurora to the naked eye oftentimes looks very gray. However, these cell phones, they're amazing. They don't care. They don't care that it's low light. They're going to pick up the color anyway. And so what might have been very ordinary when it comes to looking at aurora, or possibly just, oh, that's a cloud, pfft, nothing. Suddenly you take a shot of it and you look at your display and go, holy purple, blue, red, pink, yellow, oh my gosh, it's a rainbow, right? It's just insanely colorful. That's what cell phone cameras see. But there are, and that's wonderful. I think it's fantastic. We now get to get a lot more reporting of aurora. It means so many more people now can have aurora in their backyard and be aware of these storms. And it means that space weather comes home to so many more people than it ever has. And a lot of people have been able to check off their bucket list seeing the aurora without really even having to travel, right? Which is just wonderful. I think it's just one of the benefits of it. But remember how we talked about panic, right? What was one of the benchmarks we used to look at aurora when it came to these storms? Right? Aurora was a metric we used, wasn't it? Uh-oh. What's that mean? This is aurora guaranteed by the naked eye. See where I'm going with this? The game's changed. So suddenly, in a sense, this metric has become a moving target, and it will continue to do so. Why do I know that? Because cell phones are getting better, cameras are getting much more sensitive, and they're getting to be more of them. People are getting plugged in. So not only have our reporting ability changed, but our ability to see what was unseeable before. I am what used to be very rarely getting told by one person, Derek Wilson, on Twitter, subvisual aurora at Paradox Valley, Colorado. I remember that so many times from KP of 2, KP of 3, KP of 4, maybe not 2, but 3, 4, 5. He used to be the only one that reported subvisual aurora, and then he named it subvisual aurora, and I said, what a great name. So I picked it up. Now, in this solar cycle, I've seen probably 30, 40, 50 different sightings of subvisual aurora, where they're calling it that. So that's become a phrase, because you can't see it with your eyes, but if you take a picture of the sky, you'll see pillars on your cell phone, or on your DSLR, right? Or your mirrorless camera, your Lumix, whatever you're using. Cameras have gotten so unbelievably good. So the game has changed, and so has the metric. But that has consequences, right? Here's an example of how fast is it changing. Okay, here is predictions from 2007 through 2021. This is the number of smartphones that have been sold to end users worldwide. Notice that it plateaus, right? Grows in, and this is in millions of units, right? So you see it really ramping up in 2011, 2012, and now it's kind of plateaued. Anybody know why it's plateaued? Well, mainly because old cell phones, you don't have to buy new cell phones anymore. You can buy used ones, right? Because the used ones are still dang good. So that's why it's plateaued. It's not because people are getting sick of cell phones. It's because now there's a secondary market. You don't have to buy a brand new one. And how do you know that? Oh, yeah, and here's the second thing. Sorry, I forget how these charts work. So you can see that. Here's the peak. Here's the peak. Here is the rise to the peak of the cell phone growth industry, and then it began to decline. So have we passed the peak of the cell phone era? Well, it's clearly no, that's not true, because the number of subscriptions continues its climb. Okay, here is from 2016 to 2027. These are projected numbers out here, but it's projected to continue. And you can even see through where things began to plateau in 2014, 2015. It's not plateauing, not with subscriptions. So it's clear people are using, they're buying used cell phones. Go on eBay, you'll see it. I mean, some of these, even flip phones are still selling, but smartphones are selling over and over. Yeah. Hate to say it, me too. This is a back market. Not that I'm not sponsored by Back Market, but I've gotten a few things from them and they're great. So even I haven't bought a new cell phone recently. I bought a used one. Okay, yes, I'm cheap. No, I'm kidding. No, I just particularly like that model. Anyway, yeah, and I'll mention this too. And what's interesting too to think about when you think about, okay, not only are cell phones exploding, so pictures are exploding, but look what's the next thing that's exploding. This is the amount of traffic that we're passing through our cell phones every, month, right? These are gigabytes per month. Back in 2014, it was 1 gig a month. So you have your phone for an entire month and maybe you'd pass one gigabyte of data. This is now projected by 2027 to be over 40 gigs a month. Okay, and right now we're sitting, in about 15, maybe a little bit more than that. Okay, some of these are projected numbers. I can't tell where the projections begin. But this is what we're expected to be doing. And you know why it's such a huge rise from 1 gig to 40 gigs. It's not just that our cameras have gotten much, much more high resolution, but we're also doing video. Okay, so it's both the camera sensitivity, the camera resolution that's causing this growth, but also the fact that we're doing video now. Anytime you're doing this kind of stuff, you're getting far more visibility in what's going on. And trust me, aurora is a great thing to take videos of because it's so dynamic. The camera lens market has been projected to grow incredibly insanely, but it's really the smartphone that's taken over. And how do you know that? Look at the digital camera sales. Okay, the lens market is still growing, but the DSLRs and the mirrorless cameras, it's really kind of falling off. Why? These are beginning to compete with them now. Okay, people are beginning to take classes to learn how to be an astrophotographer with a cell phone camera. Huh? I mean, it's insane. Now, granted, these will probably never be anything like these. The optics and things are just insane. The size of the detector, the low light sensitivity, oh my goodness, it's always going to beat something like this. This is multi-purpose, this is singular purpose. But these are getting so unbelievably good that it's turning average, ordinary people into amazing photographers, which is wonderful. But when it comes to Carrington-class events and what we know and what it historically has been written about Carrington-class events when it comes to aurora sightings, uh-oh, that could lead us to trouble, right? How do I know that? How long ago was this? Do you guys remember these storms? Anybody want to correct me? Was the 23rd of March, was that a G4 or G3? I can't remember. And I didn't have time. Honestly, I was putting this stuff together like inches before, moments before I had to get online with you. So I can't remember. I didn't have time to look it up. But 23rd of March, what was that, a G3, G4? I might have touched a G4 for a moment, maybe. And then, of course, April 24th, which was not that long ago, less than a month ago, that was a G4. And then the 19th of May. How many days ago was that, guys? 2? Now, remember, Mark, you think it's a G4? Chris, G4? Matthew, G4? Okay. So 2 G4 storms and a G2, right? Are these Carrington-class events? Not even close, right? A Carrington-class event is a G5 if it's a CME hitting. We were talking about CME impacts right now. An ICME is hitting Earth, and it's slamming that KP up to 9, right? And it's off scale. And a G5 is as high as you go, and it's just pegged at G5, 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 G5 for, maybe 24 hours or so. Massive events. These, not even close. Not Carrington class. If you had a Victorian person standing next to you who had experienced the Carrington class event, and you had them standing here looking at what we're about to show, what do you think their take on it would be that these storms were? So from the March 23rd event, here's Perth, aurora, right? North Carolina, aurora. Here, look at me. Should I stand like this? I just snapped these as quick as possible. I look like a doofus. New Mexico, once again, don't look at the doofus, look at the aurora. New Mexico, right? New Mexico? How far south is that? Arizona, Phoenix? How far south is that? Amarillo, Texas. Look how tall the pillars are. If you had a Victorian person in Texas, from obviously you're not Victorian if you're in Texas, but if you had a Victorian person see how low this aurora was spotted, how do you think they'd respond? Wouldn't you think they would think that this was a G5? Right? A sustained G5. How about April? Right? So this is just a couple months ago. This is last month, right? Not even a month ago. Let's look at this one. Now this is just straight from my Twitter feed. Okay, I just grabbed a few. Where is this? Nebraska. Look how high the pillars are. What's this one? Southern Arizona. Oh, yay. Saguaro cactus with aurora. Oh, yeah, we see it all the time. Right? Death Valley? That's my latitude. Exmoor? Try to grab a few from the UK. Stonehenge. Look how high the pillars are, once again. And here's one where they're saying that 6 hours after the first hint of the northern lights in the sky, before it even turned dark, here they are in southern England. What do you think the Victorians would have thought of this? What do you think the average person who has Carrington fever thinks of these auroras? The fact that we've had multiple sets of aurora. Here's 2 storms. We've had multiple sets of aurora that were seen. And I didn't have time to grab some of my stuff because you could see it in Brittany, France. You could see it in the Alps, in Germany. Oh, in Germany. Over the skies in Germany. Did we just do Texas? Right? We did Texas in March, now we're doing Texas again in April. What is going on with the sun? Oh my God, it must be the Earth's magnetic field weakening. This has never happened before. The only time this happens is with Carrington class events. Oh my God, the kill shot is coming, we're all gonna die. Really? How about this one? Did you guys see this? China. China saw aurora. Anybody remember where the latitude of China is? And it's on the wrong side of the globe so that the auroral oval is tilted away from China. So it's really hard to see there. And yet we have aurora in China just 3 weeks ago. Carrington class event? Not even close. But what do you think the folks on YouTube are saying about this? Right? It's all because of the Earth's weakening magnetic field? Really? Has nothing to do with this, has nothing to do with the fact that the sun is now beginning to fire stronger storms than we've seen in 2 solar cycles, has nothing to do with the fact that social media now has proliferated and we have so many more people out there looking at the sky, knowing that it's coming, and therefore anticipating with cameras held at the ready. Right? Come on. No, it's all the Earth's magnetic field. We are going to die. These are kill shots. The sun is coming for us. God's wrath is upon us. No, it's really explainable. Oh, but the birds weren't chirping and the sky wasn't so bright you could read it from aurora. That's how it's different from Carrington class events. Really? This was 2 days ago, guys. Can't believe this. Again, this is in the UK. Aurora Borealis from Lancaster about 3:15 in the morning. So bright, it was like daylight. The birds were singing. Sounds like the birds probably sang a lot with aurora. We just didn't know to capture it. We didn't know it was happening. It doesn't take a Carrington class event. It takes a mild G2. This was barely a G2 2 days ago. This was actually a composite event that was a glancing blow from a CME that ended up being a little bit more of a direct hit, along with some fast solar wind. So it got caught up right in the right place to be enhanced by this stream interaction region. And it gave us a G2. And we got birds singing in the skies over Lancaster. See what's happening? So there's, yeah, like Chicken Little, the sky is falling. Isn't that amazing? Right, the China pics looks like Abitibi, Canada. Right. Victorians would be distracting everyone looking at their dresses. True. As long as they had Aurora on it, it'd be fine. I've seen it from Boston. Never thought I would, but amazing. Yes, you will, and you'll see it again, and you'll see it again, and you'll see it again. Aurora is becoming part of our world, of our daily lives, right? Because of the advent of social media, because of the advent of these cell phones, because we're just much more aware, and, nice to say, because our sun is kind of returning to its heyday. I mean, it's not going back to cycle 19. We're not even close to that. That was in the 1940s, but where we just had insane things going on. But we're back to cycle 21 for sure. Maybe cycle 22. I don't want to get ahead of myself. But we could, over the next couple cycles, get back to that. We're coming out of what was like a very Dalton-like minimum. Was it a grand solar minimum? Yes, it was. That is what a grand solar minimum, a typical grand solar minimum looks like. Sunspots don't have to disappear. The solar activity just has to diminish a little bit. Okay. And there's lots of other implications. But that's, in a nutshell, I'm not going to go into the fact that some of these, well, that was weird. Some of these events have, with smaller solar cycles, you have a bigger chance of Carrington class events, actually. That's a detail that I've talked about in the past. I'm not going to muddy the waters with that right at the moment. Except to say, actually, as we come out of the grand solar minimum and go into these higher activity cycles, we actually may be reducing our chance to have Carrington class events, believe it or not, because the sun is going to become a bit more behaved, well-behaved, more active, but more well-behaved in the sense that it's not going to be launching these extreme events nearly as often. But turns out we're going to be confused generally as a populace anyway. At least pop culture is going to be confused because suddenly aurora is everywhere and much, much brighter and much, much bigger and much, much more everything. And then when people go back and they look at these historical events and they look at where aurora was sighted and they're seeing aurora coming down nearly to the same levels and far more often, they think, oh my goodness, this is paradigm shifting. This is Armageddon on the way. No, it isn't. Society growing and our sun waking up again. So China, right? Texas, right? If we get a higher G4 or a more sustained G4, and if we had social media more down in Mexico and down in the lower latitudes, could we see it? Yes, there was a person who was actually in Florida who thought they saw aurora. And I didn't take that shot, but you could actually see it in one of my forecasts and also on my Twitter feed. Still questions out whether or not it's aurora. These cameras are getting so unbelievably sensitive now that they're pulling out air glow and making it bright enough to look like it's aurora, or even glow just from lights, either corona from lights or lights from just the reflection. It can get tough when you're trying to look at the horizon and you have a lot of light pollution in the way. So just know that these cameras are going up to the point where light pollution is becoming a bigger and bigger issue, simply because we can see so much more. But does that mean that our marker for aurora, for big Carrington class events, is going to go away? Probably. Because more and more people are going to get social media, more and more people are going to get internet, more and more people are getting cell phones, more and more aurora sightings are going to be very widespread soon. There may be a good chance that over the next couple of solar cycles, aurora is going to be something that people say, oh yeah, I saw it last week, especially during solar max. So yeah, I think I'll stop here. We won't get into the 1972 event, which is, again, the fastest Carrington class event on record. That was the one I was going to go into. What I'll do is I will go into these events I won't do it chronologically. I'll probably do it, we'll bounce back and forth in time a little bit. And the reason for that is because there's going to be certain events that I want to place together because they have certain phenomena. As we have learned, as I go back here Sorry, all this junk. Bum, 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 bum. Oh, good Lord. Here. Well, I guess I could use this one too. As we've learned, there's these different effects, right? These different categories by which we analyze things. And so different storms are going to be bigger deals in certain areas than in others. And so some of the events that we'll go through will be Carrington class in one area or maybe several areas, but not all. Okay, and then there will be some events that you've never heard of because honestly, they were only Carrington class in just one specific arena. And they caused a very specific but very impactful response. I want to say impactful response, an impactful, effect that really has strong implications for our technology and how we grow technologically as a society. But I'll bet you, by the time we're done with this series, what you'll see, what you'll learn, is not only are there a ton of these events. What do I want to do? Let me see. Let me get out of this for a second. I think there's a slide I wanted to show. This one? Yeah. As you can see, I've got lots of slides. Not only are there a ton of these events, right, and this is just under one metric, but there's going to be a lot of events that you've not ever heard of. And so I'm going to, probably with the Patreon family, I'm going to pick and choose. We're going to pick and choose which events we look at. Some of them I'll want to talk about specifically because of the impacts they have, but others can be ones that are points of interest to the general, to us, and we can just dig into them as we go. But one thing I want to make sure that we understand from this point of view is how unbelievably silly and emotion-based this kind of definition of a Carrington class event is. And hopefully, I've given you that understanding. I've given you a much better appreciation so that when you see all of these names, and I'm sure a plethora of names I have not included on this list, but could probably be categorized in here somehow. And you look at photos or news articles or videos, even by people who have, multiple letters behind their names. I'm not going to call out anyone in particular, but there are many, sadly, because it's been conditioned. This junk food has been conditioned into us. We've been eating it for years, not realizing that it's junk food. And so it's taken over when it comes to these Carrington class events. And it's emotional. This is emotional, right? All of this, emotional. Bad. Fire bad, fire bad. If anybody remembers that Camp Chaos thing. This is the way we need to do it. And when we really start taking apart these events in a piecewise and quantitative fashion, we find out that Carrington classes, it's tricky. It's tricky to define it. And not one event takes the gold in all categories. But the 1859 event is on the podium for all categories, which is why it's very well remembered and very well studied. The interesting thing is that as we go through this process, you will see that there are other events that had one little thing been different, that could have easily have taken the cake. That one could have easily been the reason, the benchmark event. And you'll see that in the next, as a matter of fact, you'll see the beginning of that in the next class, because we'll be talking about how that works. Okay, so hopefully this has been good. I see lots of Tan with the Scoves. So, yeah, Hollywood distortion, surely not. Who's defined Carrington as a micronova? I've seen it over and over again. Are you kidding? Comments, oh gosh. You're very welcome. Calming the hysterics, you're very welcome. It's scrolling too fast, I didn't see who wrote that. Lucky says, do you have an opinion on the dagger model? Oh yeah, I remember someone talking about it. The claim is it predicts a solar storm 30 minutes before it happens. 30 minutes before it happens means 30 minutes before it hits Earth, not 30 minutes before it launches from. And there's lots of models out like that. And I actually sat on a NASA panel recently that addressed some of that. So yeah, I won't talk about it in this situation, but yes, I am familiar with the Dagger model. And no, and I'm sorry, Oaks Hill Classroom. No, I'm not saying the grid will be just fine. I talked about that. And go look at my other courses. The grid is not necessarily fine. There are events in which things are issues. So I don't know where you get that. Anyway, the Dagger model is just one of many. And yes, it has promise. Thank you for the amazing, this is Matthew. Thank you for the amazing, and yes, Sunny, thank you. Thank you for the amazing analysis and information and taking the time to make and explain it so well. I'm so glad you liked it and it was clear. Oh, yeah, the madness you've been conditioned to live in. Yes, I saw that. That's so awesome. Yeah, exactly. We've been conditioned to live in madness. And you're claiming it can never happen again. Oak Hill, you're about to get booted because you are completely missing everything. You need to go back, take off your blinders, and listen to what I'm saying. I never said they don't happen, they can never happen again. It happens all the time. I just showed a whole list of things. I'm saying the Carrington event happens a lot more often than you might realize. So where are you getting that? Go back and actually listen to the words instead of what you want to hear. Yeah, Lucky, yeah, I got that Dagger model. It has promise. There are other ones that have promise too. So, you know, there's a lot of space weather centers that are coming up that are trying to break through that new technology. They're going to be years out yet, though, because they have to transition things from research to operations. That's the problem. It takes a lot of testing, and there's a lot of money that has to be done, and it's interdisciplinary with lots of institutions involved. So it's a slow process. Is it going to happen before the end of the cycle? Maybe. Is it going to happen by Solar Max? Hell no. It's a slow process. So just be patient, and you'll see more about it. About the Dagger as well as Fire and a couple others that are really coming up the ranks, really, really good ones. Especially with machine learning, it's just amazing. During an SID, this is Tom, why does low frequency propagation get enhanced to 20 kilohertz? Because you're creating a layer, an atmospheric layer. And if you're talking about skywave, it also depends upon what are you talking about. Are you talking about skywave at 200 kilohertz? I need to understand what you're talking about. The repeater, be a little bit more specific, and I'll be able to answer that better. But it has to do with the fact that you're creating more layers and you're creating better ionization in the upper atmosphere. I missed it about how do you feel about NASA? I can't read it. It went too fast. Great information. Oh, you're welcome, Andy. Thank you so much. 1,000 thanks, Purple Rain. Oh, thank you so much. I'm so glad it was very good. Be very suspicious of the fear porn channels. Yes, Secret Owl, you are absolutely right. Don't let it drive you into anxiety. Things are moving too fast. I'm not being able to see everything. Sorry about that. Hi, Spirit. Tamitha has many NASA colleagues, and we don't say bad things. That's right. Right. I have lots of NASA colleagues, and it's not that I don't say bad things about them. It's just that I hear from them when I do. But I will call them out, and they know it. And I'll also admit when I'm wrong. So when people correct me, who are scientists, they correct me, and I do my best to state truth. And yes, I lean toward mainstream. I don't lean toward fringe. Fringe, and the reason why is not because I don't dislike fringe. I actually love fringe. I think fringe and mainstream need to be working more hand in hand and not be suspicious of one another. Because, as I've said many times before, fringe gives mainstream wings, but mainstream keeps fringe grounded. So they both have a place at the table, and we just need to be cognizant of their different roles, and that's all. That's all I say about it. Okay, Adam, because the VLF spectrum from 3 hertz, poop, has much to an scroll too fast. I'm sorry. Try it one more time. Okay. 20 kilohertz. Oh, thank you, Mark. 20 kilohertz is a very low frequency, more ground wave than sky. So why is it enhanced? I don't know if it's a ground wave. That is strange. I don't know, because that's a direct. Heart rhythmias yourself. Oh, that's sweet. Thank you, Cheyenne. I appreciate that. Okay, yes. Matthew Shipley has a very good space weather channel. Yes, he does. he's a great resource. So please go there. Purple Rain, thank you. Wonder Woman, you're funny. Skip can pick up at VLF, but higher HF frequencies can get you wiped out by a flare. Yes, so hopefully some of that conversation is going on about the 20 kilohertz. There's a lot of very savvy amateur radio operators in here, as well as ionospheric physicists. So, you know, you might ask the questions in there, especially if I keep missing it. Clickbait sells media. You're right, guys. You're right. Yeah, okay, yeah, things are scrolling super fast. VLF radio can be used for digital radio broadcasting for voice, such as digital using LSB and USB. Yeah, and yeah, there's lots of reasons to use VLF, and it does get affected. People think that it doesn't get affected, but it really does. I know a lot of people that talk about VLF getting affected very early by the flares. It's incredibly sensitive, especially to magnetic crochets. And I don't know the details. It's just a little bit out of my expertise because I don't study those frequencies. Okay, yes, typically underwater, right? Talking to U.S. nuclear submarines because VLF travels underwater, which is great. Very good night from Spain. Okay, Costa Verde, thank you for joining. Yeah, because this is where I'm going to stop for the evening. So if you guys have questions, I'll take questions for a little bit longer. I'm going to check Patreon here for a second for questions, but hopefully everybody enjoyed this. And let me check. Let's see. Oh, Chris, thank you. I'm seeing right now. This has been wonderful and looking forward to the follow-on courses. Good. I'm so glad you enjoyed it, Chris. Thank you so much. Oh goodness, Ben's net worth is over 300K. Okay, great. I wish he'd stop bashing scientists because they've made him rich. It's very clear. Lourdes was sorry to miss, but she'll watch later. Yeah, that's so sweet. Thank you, Chris. I appreciate you saying that and letting me know that. Let's see. You totally missed it live, but go back and watch it. Yeah, it's a good one. It's a good one. But you know, I purposely call this stuff out because it's too emotional, and it's not quantitative, right? And yeah, it gets you clicks and it gets you rich. I'm not here for that. I'm here to teach. I'm here to show you sanity, right? So you can get through your day. All right, let me check. Oh no. Okay. Well, no, I'm not going to talk. I'm not going to address Ben. Ben does what he does, and I appreciate the fringe work that he does. Anybody on Patreon? Let me just double check to see if there are questions. Do you guys have questions on Patreon? John Luck says, when you are talking about the degrees of ejection from the sun, is that normal to the surface? So we're talking about going back about the drunken sailor. Normal to the surface. Yes, it's normal to the surface of the sun. So it's perpendicular. So we're assuming that the flare is shooting straight out of the sun. So obviously if the flare were on the north pole of the sun, the gun would shoot straight up, which is normal to the surface of the sun at that point. So yes, normal to the surface, and really all we're talking about is the rotation of the sun. So if my nose is shooting something straight out on the sun, the nose is shooting a flare straight out, as my nose rotates, right, as the sun rotates and my nose rotates it with it, I'm always shooting something straight out of my nose. So it's normal to that surface, and that's how we get the degrees on that one diagram, this diagram, how we get the observer flare angle, right? And it can be a cone because, and the reason why we talk about it being a cone, because if the flare only at the equator of the sun, is it going straight at the Earth-Sun line? If the solar flare is at the, my forehead, for instance, the pimple that we were talking about before is on my forehead somewhere, then it's going to be shooting out this way. So, that's what I mean by the gun going this like this, because the surface of my forehead is kind of, and a sphere is curved. So it's going to point that gun up and down as well as side to side. So that's why I said it carves out a cone of about 30, in this case, 35 degrees, right, all around So that's the drunken sailor. That could be if the sunspots that are shooting the flares out are in the northern hemisphere, the gun's going to be pointed above you. If the solar flares shooting, pimples are down here, then the gun is going to be below Earth, right? So yeah, so that's the normal to the surface. So yes, John, hopefully that answered that question. Let me see what else we've got. Bart Pulverman asks, if the Earth's magnetic field is pulled back, does it affect magnetic compass readings at various latitudes compared to the normal? Yes, and the reason why is because reading a compass, if it's sensitive enough to catch horizontal components, you'll see that compass be wiggling a little bit during geomagnetic storms, during big ones, which is partly why, for instance, people worry about when they go into the South Atlantic anomaly and the magnetic anomalies that occur. People wonder, is that part of the Bermuda Triangle, so to speak? And the South Atlantic anomaly is often called the Bermuda Triangle of space. And part of that is because of all the particle precipitation that goes in there. But part of it also is because the magnetic anomalies the magnetic field is so different in that region and weak in that region that is it more susceptible to wiggles and changes, and so it causes ships and navigation, especially for maritime, causes the navigation to be off. Don't know, but it's something that I think would be fun to look into, and I know that there are definitely some researchers who've been looking into that. But those areas are just always so strange. Some people here have had personal experiences with them, and it's just a very strange area, and I'm not sure people like to necessarily live in those regions because weird things happen that are hard to quantify. So could you have those types of issues? Yes, absolutely. And as the Earth's magnetic field continues to change, is that changing our compasses, and is it going to eventually make the compass that we use today, unusable? Yeah, likely. Unusable, you can still use it, of course. It's not going to cause a compass not to function. It's just not going to read anything that is worthwhile. So eventually we'll have to change that. And it's going to get very interesting here over the next, several hundred to 1,000 years. Too bad we won't necessarily be around to see it. Plus, with the weakening of the Earth's field, some geologists are not completely convinced that it's actually the pole is actually flipping, because we've seen these weakened excursions before in the historical record, and then the field comes back. So it may not be a pole flip. It may just be one of these anomalies where the Earth field weakens for a little while and then it comes back. The Earth's dynamo is not much better understood than the sun's dynamo, sadly. So, magnetic fields are tricky. They're tricky. All right, let me see what else questions we have. Oh, you have a sensitive compass. John answered my question. I have a sensitive compass that oscillates during these solar storms about 2 to 4 degrees. There you go. That is awesome. So there's even a conversation going on Patreon right now. That's really cool. Marty says, thank you for solid grounding in space weather. Jerry says, super presentation. Thank you. Bart says, I think this is one of the best I've done. Aw, that is so, oh good. He was able to completely understand my explanations. That is so great. Never saw aurora. In spite of the fact that I frequently look for it in the winter, I'm a retired professional photographer, and as much as I've rejected smartphone technology, I've just decided to upgrade my cell phone to one with top quality. Which one do you think is the best one for aurora? Oh my goodness. Who can help? Who can help Bart? Whether you're a Patreon member or anywhere else, if you can help Bart and know which is the best. Mine, I use, and I don't use it for aurora, obviously, but I love my Samsung. Samsung Galaxy's got just amazing. This is a 21, S21. But I'm sure tons of people have ideas of what you would think the best cell phone is for aurora photography. I bet you someone could write a book on that. That'd be a really, really good book. Obviously, you'd have to make revisions very quickly because cell phone technology changes so fast that there are probably tons of you'd have to write new editions because there'd be tons of changes and lots of competitive options out there. But that would be a neat book to write, actually, and I bet you they'd be a really good seller. So anybody who wants to take that and run with it, hey, feel free, right? That you could probably get a lot of reads off of that, knowing what is the best cell phone for aurora. And there'd be a lot of reasons why, right? Control over the aperture and the ISO and shutter speeds and stability and, you know, all sorts of things that would give you different reasons to like it for aurora instead of, let's say, some other type of photography. That's a neat concept. So thank you, Bart. Hopefully somebody will mention what they use. Yeah, I see you have Adam has an S22 Ultra, just space weather related. Yeah, that would be very cool. Other people have Samsung 22. Yeah, other people use iPhones. I know iPhones have really great low light sensitivity. Samsung Galaxy is rated higher in photography. This is Matthew Shipley saying this at the moment on comparison sites. Not sure how that will translate to aurora. Right. What a neat, what a neat thing to consider doing a cell phone shootout, especially during Solar Max, guys. So anybody who wants to do that, hey, do it. You got a YouTube channel or a video or something like that you're going to do a shootout between different cell phones for aurora photography. Wow, I'd watch it. I'd probably promote it. So let me know. Let me know if you do it. That'd be awesome, because that would be very, very helpful to lots of people. So thanks, guys. Okay, any other questions? I think I got through all the ones on Patreon. Let me just refresh one more time to be sure. Let's see. Yep, got through all those. Okay, guys. Any other last questions before we bid you, or before I bid you adieu? It's been 3 hours and almost 20 minutes. So this is about another average mini course for us. How much does Elon Musk have to worry about his Starlink and that bad space weather? A lot, as he's learning. And that's actually something that we'll talk about later. We will. That's one of the storms that I will do a comparison with when it comes to Carrington, like certain events. There's an event in 1967 which is quite interesting with low Earth orbiting satellites, which is among other things, it was a benchmark for me, especially when I worked at the Aerospace Corporation. It was where I first learned about how bad drag was for low Earth orbiting satellites, and there was a lot we learned about how space weather inflates the upper atmosphere and how that's a big problem back from that 1967 storm, among others. And I've been, anybody who took my courses at Millersville or saw me do mini courses, I've been talking about Starlink falling out of the sky for years, way back in Solar Minimum, saying, get ready, it's going to happen. And so it's still an issue. But the nice thing is that Elon Musk knows that, SpaceX knows that. They not only work with NOAA and Sue Wei, who's a fantastic scientist. She does all the WAM IPE stuff. She's on it, man. She's working with them, and a great gal too. I got the fortune to meet her this year at the Space Weather Workshop, and she's just really, really wonderful gal, and very, very brilliant. So I'm very happy that she's able to work, and she and her team are able to work with Starlink and obviously Blue Origin and half a dozen other of these startups, because we don't really want their birds falling out of the sky. That would be sad, not to mention costly. And they're paying attention. And all it takes is orbit raising, just more fuel. If you really want to fight it, okay, fine, you do that. But you can also just insert at a higher altitude and just be more aware. It's easy solution. Easy solution. Same thing with solar flares and communication issues with solar radio bursts. Launch at night. Just launch at night. As a matter of fact, I think we have a launch. Don't we have a launch today? Hopefully they didn't scrub it. It looks like the X flares are dying down, and I haven't seen big radio bursts. So hopefully the Artemis, not the Artemis, but the launch to the ISS today will continue. Okay, guys. Any other questions? Imagine that Starlink falling on your heads. Yeah, that's what I don't want. I definitely don't want that. That's for sure. Oh, yeah. That was the other thing. Starlink does, when you have big radio bursts, especially that we had a couple big radio bursts about a couple weeks ago, and I didn't put that on this channel, but I had it on tomorrow, a quick space weather shorty, that we're looking at radio bursts up to 16 gigahertz, and that does people were talking when I was doing a live briefing a couple weeks ago. They're saying that their Starlink ping times were dying, and I was like, really? I should go look at that. So when I looked and saw how big the radio bursts were, it made sense, because Starlink squawks at 12 gigahertz, and the sun was actually firing, screaming at 16, and below. And so, yeah, that makes sense. The sun was screaming louder than Starlink satellites. Of course it was. And so that was probably the issue for the ping times, is that if you happen to be trying to access the internet right when those solar flares were going off and those radio bursts were hitting you, well, it's going to make you wait, right? And depending upon how long and luckily there weren't too many of them that had radio bursts at that frequency, and they didn't last all that long. But there were some that lasted, a few 5 minutes or so. So if you were doing critical work and really needed internet at that time, you didn't get it. So that's why people were upset. I remember the other day, and that's just going to happen, especially during solar max. I mean, this is what we have to deal with. The sun can, it doesn't damage anything, but it is a minor inconvenience. Like I've said so many times, right? Space weather, it's a mild inconvenience most of the time, and that's just what it is. Okay, guys, the last Australian, like your name. The great show, Tamitha, with the human primates exploding over 2,000 nuclear devices in the 40s. Oh, good. Does that destroy the atmosphere, letting more radiation in? It probably destroyed our ozone layer, and we'll talk about how space weather actually does that too. Space weather is actually pretty impactful when it comes to radiation dose. Starfish and all that stuff, oh goodness. That's a whole nother bag of nightmare to get into. And the impacts from that and all the upper, above ground A-bomb testing and, or whatever testing we did. We did a lot of nuclear testing. We were really stupid in the 40s and 50s, which we realized how stupid we were. There's a lot to be said about that, but that's all high energy physics and not really relevant to our discussion here. But yeah, there are lots of impacts to the atmosphere. Nice thing is the atmosphere anneals. It does fix itself. We have oceans that help, replenish a lot of the stuff that we lose, which is probably why Mars doesn't have an ocean anymore, right? Because it lost all of its stuff to space over time. But again, a different subject. Am I going to talk? Okay, wait, I missed it. Am I going to talk more about how they're trying to fix it? Fix what, Jason? Fix how we deal with space? I don't know what that was about. Oh yeah, right. XM Sirius Radio. Yes, exactly. It's in a tundra. It might still be in a tundra. I don't know if it's still in tundra orbit, but it's definitely affected by SEPs and as well as radio bursts. Absolutely. And so Sirius, it's going to have these issues, just like DirecTV does during big solar flares with radio bursts. Yeah, I don't know what frequency. I forget what frequency it is, but I do think it's in the L band, which means it's only 1 to 2 gigahertz. It's pretty low, so it's going to have issues. Starlink's falling on my head. That's cute. That's funny. That's a funny song. Okay, guys. It looks like we're good. I think that's about it. Thanks, guys. Thanks so much. I appreciate all the questions. It was really good dialogue today, and I'm so glad you liked the show, the mini course. Remember, none of this stuff. No emotion. Emotional stuff is fun for Hollywood, but we need more quantitative. Okay. So, all right, guys. See you next time. And we'll dive into more really big events, okay? Take care.